A photograph is shown of a pond formed in a sinkhole. Layers of limestone with trees and shrubs surround the murky green water of the pond. Figure 14. One sinkholes such as this are the result of reactions between acidic groundwaters and basic rock formations, like limestone. Credit, modification of work by Emil Canel. Chapter outline. 14. 1 Bronsted-Lowry acids and bases. 14. 2 pH and pOH. 14. 3 relative strengths of acids and bases. 14. 4 hydrolysis of salts. 14. 5 polyprotic acids. 14. 6 buffers. 14. 7 acid-base titrations. Liquid water is essential to life on our planet, and chemistry involving the characteristic ions of water, H+ and OH, is widely encountered in nature and society. As introduced in another chapter of this text, acid-base chemistry involves the transfer of hydrogen ions from donors' acids to acceptors' bases. These H+ transfer reactions are reversible, and the equilibria established by acid-base systems are essential aspects of phenomena ranging from sinkhole formation, figure 14. 1. To oxygen transport in the human body. This chapter will further explore acid-base chemistry with an emphasis on the equilibrium aspects of this important reaction class. Learning objectives. By the end of this section, you will be able to identify acids, bases, and conjugate acid-base pairs according to the Bronsted-Lowry definition. Write equations for acid and base ionization reactions. Use the ion product constant for water to calculate hydronium and hydroxide ion concentrations. Describe the acid-base behavior of amphiprotic substances. The acid-base reaction class has been studied for quite some time. In 1680, Robert Boyle reported traits of acid solutions that included their ability to dissolve many substances, to change the colors of certain natural dyes, and to lose these traits after coming in contact with alkali-base solutions. In the 18th century, it was recognized that acids have a sour taste, react with limestone to liberate a gaseous substance, now known to be CO2, and interact with alkalis to form neutral substances. In 1815, Humphrey Davy contributed greatly to the development of the modern acid-base concept by demonstrating that hydrogen is the essential constituent of acids. Around that same time, Joseph Louis Gay-Lussac concluded that acids are substances that can neutralize bases, and that these two classes of substances can be defined only in terms of each other. The significance of hydrogen was re-emphasized in 1884 when Svante Arrhenius defined an acid as a compound that dissolves in water to yield hydrogen cations, now recognized to be hydronium ions, and a base as a compound that dissolves in water to yield hydroxide anions. Johannes Bronsted and Thomas Lowry proposed a more general description in 1923 in which acids and bases were defined in terms of the transfer of hydrogen ions, H+. Note that these hydrogen ions are often referred to simply as protons, since that subatomic particle is the only component of cations derived from the most abundant hydrogen isotope, 1H. A compound that donates a proton to another compound is called a Bronsted-Lowry acid, and a compound that accepts a proton is called a Bronsted-Lowry base. An acid-base reaction is, thus, the transfer of a proton from a donor, acid, to an acceptor base. The concept of conjugate pairs is useful in describing Bronsted-Lowry acid-base reactions and other reversible reactions as well. When an acid donates H+, the species that remains is called the conjugate base of the acid because it reacts as a proton acceptor in the reverse reaction. Likewise, when a base accepts H+, it is converted to its conjugate acid. The reaction between water and ammonia illustrates this idea. In the forward direction, water acts as an acid by donating a proton to ammonia and subsequently becoming a hydroxide ion, O-, the conjugate base of water. The ammonia acts as a base in accepting this proton, becoming an ammonium ion, NH4+, the conjugate acid of ammonia. In the reverse direction, a hydroxide ion acts as a base in accepting a proton from ammonium ion, which acts as an acid. This figure has two rows. In both rows, a chemical reaction is shown. In the first, structural formulas are provided. In this model, in red, an H atom is connected to an F atom with a single bond. The F atom has pairs of electron dots at the top, right, and bottom. This is followed by a plus sign, which is followed in blue by an O atom, which has H atoms singly bonded above and to the right. The O atom has pairs of electron dots on its left and lower sides. A double arrow follows. To the right, in brackets, is a structure with a central O atom in blue, with blue H atoms singly bonded above and to the right. A pair of blue electron dots is on the lower side of the O atom. To the left of the blue O atom, a red H atom is singly bonded. This is followed by a plus sign and an F atom in red with pairs of electron dots above, right, below, and to the left. This atom also has a superscript negative sign. The reaction is written in symbolic form below. HF is labeled in red below as acid. This is followed by plus H subscript 2O, which is labeled in blue below as base. A double-sided arrow follows. To the right is H subscript 3O superscript plus, which is labeled in blue below as acid. This is followed by plus and F superscript negative. The label below in red reads base. The reaction between a Bronsted-Lowry acid and water is called acid ionization. For example, when hydrogen fluoride dissolves in water and ionizes, protons are transferred from hydrogen fluoride molecules to water molecules, yielding hydronium ions and fluoride ions. This figure has two rows. In both rows, a chemical reaction is shown. In the first, structural formulas are provided. In this model, in red, is an O atom which has H atoms singly bonded above and to the right. The O atom has lone pairs of electron dots on its left and lower sides. This is followed by a plus sign. The plus sign is followed, in blue, by an N atom with one lone pair of electron dots. The N atom forms a double bond with a C atom, which forms a single bond with a C atom. The second C atom forms a double bond with another C atom, which forms a single bond with another C atom. The fourth C atom forms a double bond with a fifth C atom, which forms a single bond with the N atom. This creates a ring structure. Each C atom is also bonded to an H atom. An equilibrium arrow follows this structure. To the right, in brackets, is a structure where an N atom bonded to an H atom, which is red, appears. The N atom forms a double bond with a C atom, which forms a single bond with a C atom. The second C atom forms a double bond with another C atom, which forms a single bond with another C atom. The fourth C atom forms a double bond with a fifth C atom, which forms a single bond with the N atom. This creates a ring structure. Each C atom is also bonded to an H atom. Outside the brackets to the right is a superscript positive sign. This structure is followed by a plus sign. Another structure that appears in brackets also appears. An O atom with three lone pairs of electron dots is bonded to an H atom. There is a superscript negative sign outside the brackets. Under the initial equation is this equation. H subscript 2 plus C subscript 5 NH, subscript 5 equilibrium arrow C subscript 5 NH, subscript 6 superscript positive sign plus OH superscript negative sign. H subscript 2O is labeled acid in red. C subscript 5 NH subscript 5 is labeled base in blue. C subscript 5 NH subscript 6 superscript positive sign is labeled acid in blue. OH superscript negative sign is labeled base in red. Base ionization of a species occurs when it accepts protons from water molecules. In the example below, pyridine molecules C5NH5 undergo base ionization when dissolved in water, yielding hydroxide and pyridinium ions. This figure has two rows. In both rows, a chemical reaction is shown. In the first, structural formulas are provided. In this model, in red, is an O atom which has H atoms singly bonded above and to the right. The O atom has lone pairs of electron dots on its left and lower sides. This is followed by a plus sign. The plus sign is followed, in blue, by an N atom with one lone pair of electron dots. The N atom forms a double bond with a C atom, which forms a single bond with a C atom. The second C atom forms a double bond with another C atom, which forms a single bond with another C atom. The fourth C atom forms a double bond with a fifth C atom, which forms a single bond with the N atom. This creates a ring structure. Each C atom is also bonded to an H atom. An equilibrium arrow follows this structure. To the right, in brackets, is a structure where an N atom bonded to an H atom, which is red, appears. The N atom forms a double bond with a C atom, which forms a single bond with a C atom. The second C atom forms a double bond with another C atom, which forms a single bond with another C atom. The fourth C atom forms a double bond with a fifth C atom, which forms a single bond with the N atom. This creates a ring structure. Each C atom is also bonded to an H atom. Outside the brackets to the right is a superscript positive sign. This structure is followed by a plus sign. Another structure that appears in brackets also appears. An O atom with 3 lone pairs of electron dots is bonded to an H atom. There is a superscript negative sign outside the brackets. To the right is the equation. K equals C subscript 5NH subscript 6 superscript positive sign, OH superscript negative sign, all divided by C subscript 5NH subscript 5. Under the initial equation is this equation. H subscript 2 plus C subscript 5NH subscript 5 equilibrium arrow C subscript 5NH subscript 6 superscript positive sign plus OH superscript negative sign. H subscript 2O is labeled acid in red. C subscript 5NH subscript 5 is labeled base in blue. C subscript 5NH subscript 6 superscript positive sign is labeled acid in blue. OH superscript negative sign is labeled base in red. The preceding ionization reactions suggest that water may function as both a base, as in its reaction with hydrogen fluoride, and an acid, as in its reaction with ammonia. Species capable of either donating or accepting protons are called amphiprotic, or more generally, amphoteric, a term that may be used for acids and bases per definitions other than the Bronsted-Lowry one. The equations below show the 2 possible acid-base reactions for 2 amphiprotic species, bicarbonate ion and water. HCO3, letter 1D44, letter 1D45E, plus H2O, letter 1D459, Co32, letter 1D44, letter 1D45E, plus H3O+, letter 1D44, letter 1D45E. HCO3, letter 1D44, letter 1D45E, plus H2O, letter 1D459 H2CO, 3, letter 1D44, letter 1D45E, plus O, letter 1D44, letter 1D45E. The first equation represents the reaction of bicarbonate as an acid with water as a base, whereas the second represents reaction of bicarbonate as a base with water as an acid. When bicarbonate is added to water, both these equilibria are established simultaneously, and the composition of the resulting solution may be determined through appropriate equilibrium calculations, as described later in this chapter. In the liquid state, molecules of an amphiprotic substance can react with one another as illustrated for water in the equations below. This figure has 2 rows. In both rows, a chemical reaction is shown. In the first, structural formulas are provided. In this model, in purple, O atom which has H atoms singly bonded above and to the right. The O atom has pairs of electron dots on its left and lower sides. This is followed by a plus sign, which is followed in green by an O atom which has H atoms singly bonded above and to the right. The O atom has pairs of electron dots on its left and lower sides. A double arrow follows. To the right, in brackets, is a structure with a central O atom in green, with green H atoms singly bonded above and to the right. A pair of green electron dots is on the lower side of the O atom. To the left of the green O atom, a purple H atom is singly bonded. Outside the brackets to the right is a superscript plus. This is followed by a plus sign and an O atom in purple with pairs of electron dots above, left, and below. An H atom is singly bonded to the right. This atom has a superscript negative sign. The reaction is written in symbolic form below. H subscript 2O is labeled in purple below as acid subscript 1. This is followed by plus H subscript 2O, which is labeled in green below as base subscript 2. A double-sided arrow follows. To the right is H subscript 3O superscript plus, which is labeled in green as below in as acid subscript 2. This is followed by plus and O with pairs of dots above, below, and to the left with a singly bonded H on the right with a superscript negative. The label below in purple reads, base subscript 1. The process in which like molecules react to yield ions is called autoionization. Liquid water undergoes autoionization to a very slight extent. At 25 degrees C, approximately 2 out of every billion water molecules are ionized. The extent of the water autoionization process is reflected in the value of its equilibrium constant, the ion product constant for water, Kw. H2O, letter 1d459, plus H2O, letter 1d459 H3O plus, letter 1d44, letter 1d45E, plus O minus, letter 1d44, letter 1d45E, letter 1d43W equals H3O plus O minus. The slight ionization of pure water is reflected in the small value of the equilibrium constant. At 25 degrees C, Kw has a value of 1 times 10⁻14. The process is endothermic, and so the extent of ionization and the resulting concentrations of hydronium ion and hydroxide ion increase with temperature. For example, at 100 degrees C, the value for Kw is about 5-6 times 10⁻13, roughly 50 times larger than the value at 25 degrees C. Example 14. 1. Ion concentrations in pure water. What are the hydronium ion concentration and the hydroxide ion concentration in pure water at 25 degrees C? Solution. The autoionization of water yields the same number of hydronium and hydroxide ions. Therefore, in pure water, H3O plus equals O minus equals X at 25 C. Letter 1d43W equals H3O plus O minus equals letter 1d465. Letter 1d465 equals letter 1d465 2 equals 1. 0 times 10⁻14. So, letter 1d465 equals H3O plus equals O minus equals 1. 0 times 10⁻14 square equals 1. The hydronium ion concentration and the hydroxide ion concentration are the same, 1 times 10⁻7 m. Check your learning. The ion product of water at 80 degrees C is 4 times 10⁻13. What are the concentrations of hydronium and hydroxide ions in pure water at 80 C? Answer, H3O plus equals O minus equals 9 times 10⁻7 m. Example 14, 2. The inverse relation between H3O plus and O minus. A solution of an acid in water has a hydronium ion concentration of 2 times 10⁻6 m. What is the concentration of hydroxide ion at 25 degrees C? Solution. Use the value of the ion product constant for water at 25 C. 2H2O, letter 1d459 H3O plus, letter 1d44, letter 1d45E, plus O minus, letter 1d44, letter 1d45E, letter 1d43W equals H3O plus O minus equals 1. 0 times 10⁻14. To calculate the missing equilibrium concentration. Rearrangement of the Kw expression shows that O minus is inversely proportional to H3O plus. O minus equals letter 1d43W H3O plus equals 1. 0 times 10⁻142. 0 times 10⁻6 equals 5. 0 times 10⁻9. Compared with pure water, a solution of acid exhibits a higher concentration of hydronium ions due to ionization of the acid and a proportionally lower concentration of hydroxide ions. This may be explained via Le Chatelier's principle as a left shift in the water autoionization equilibrium, resulting from the stress of increased hydronium ion concentration. Substituting the ion concentrations into the Kw expression confirms this calculation, resulting in the expected value. Letter 1d43W equals H3O plus O minus equals 2. 0 times 10⁻6, 5. 0 times 10⁻9 equals 1. 0 times 10⁻14. Check your learning. What is the hydronium ion concentration in an aqueous solution with a hydroxide ion concentration of 0? 1 m at 25 degrees C. Answer, H3O plus equals 1 times 10⁻11 m. Example 14. 3. Representing the acid-base behavior of an amphoteric substance. Write separate equations representing the reaction of HSO3-, A as an acid with O-, B as a base with H high. Solution. A HSO3- letter 1d4 4 letter 1d4 5e, plus O minus, letter 1d4 4 letter 1d4 5e, so 32 minus, letter 1d4 4 letter 1d4 5e, plus H2O, letter 1d4 59. B, HSO 3 minus, letter 1d4 4 letter 1d4 5e, plus high letter 1d4 4 letter 1d4 5e, H2SO 3, letter 1d4 4 letter 1d4 5e, plus I minus, letter 1d4 4 letter 1d4 5e. Check your learning. Write separate equations representing the reaction of H2PO4 minus, A as a base with HBr, B as an acid with O minus. Answer: A H2PO4 minus, letter 1d4 4 letter 1d4 5e, plus HBr, letter 1d4 4 letter 1d4 5e H, 3PO4, letter 1d4 4 letter 1d4 5e plus Br minus, letter 1d4 4 letter 1d4 5e. B H2PO4 minus, letter 1d4 4 letter 1d4 5e, plus O minus, letter 1d4 4 letter 1d4 5e HPO 42 minus, letter 1d4 4 letter 1d4 5e plus H2O, letter 1d4 59. Learning objectives. By the end of this section, you will be able to explain the characterization of aqueous solutions as acidic, basic, or neutral, express hydronium and hydroxide ion concentrations on the pH and pOH scales, perform calculations relating pH and pOH. As discussed earlier, hydronium and hydroxide ions are present both in pure water and in all aqueous solutions, and their concentrations are inversely proportional as determined by the ion product of water, Kw. The concentrations of these ions in a solution are often critical determinants of the solution's properties and the chemical behaviors of its other solutes, and specific vocabulary has been developed to describe these concentrations in relative terms. A solution is neutral if it contains equal concentrations of hydronium and hydroxide ions, acidic if it contains a greater concentration of hydronium ions than hydroxide ions, and basic if it contains a lesser concentration of hydronium ions than hydroxide ions. A common means of expressing quantities that may span many orders of magnitude is to use a logarithmic scale. One such scale that is very popular for chemical concentrations and equilibrium constants is based on the p function, defined as shown where x is the quantity of interest and log is the base 10 logarithm. Px equals minus log x. The pH of a solution is therefore defined as shown here, where H3O plus is the molar concentration of hydronium ion in the solution. pH equals minus log H3O plus. Rearranging this equation to isolate the hydronium ion molarity yields the equivalent expression. H3O plus equals 10 minus pH. Likewise, the hydroxide ion molarity may be expressed as a p function, or pOH. pOH equals minus log O minus, or O minus equals 10 minus PO. Finally, the relation between these two ion concentration expressed as p functions is easily derived from the Kw expression. Letter 1d43W equals H, 3O plus O minus. Minus log letter 1d43W equals minus log H, 3O plus O minus equals minus log H, 3O plus minus log O minus. P letter 1d43W equals pH plus pOH. At 25 degrees C, the value of Kw is 1 times 10 minus 14, and so 14 equals pH plus PO, as was shown in example 14. 1. The hydronium ion molarity in pure water or any neutral solution is 1 times 10 minus 7 m at 25 degrees C. The pH and pOH of a neutral solution at this temperature are therefore pH equals minus log H, 3O plus equals minus log 1. 0 times 10 minus 7 equals 7. pOH equals minus log O minus equals minus log 1. And so, at this temperature, acidic solutions are those with hydronium ion molarities greater than 1 times 10 minus 7 m and hydroxide ion molarities less than 1 times 10 minus 7 m, corresponding to pH values less than 7 and pOH values greater than 70. Basic solutions are those with hydronium ion molarities less than 1 times 10 minus 7 m and hydroxide ion molarities greater than 1 times 10 minus 7 m, corresponding to pH values greater than 7 and pOH values less than 7. 0. Since the autoionization constant Kw is temperature dependent, these correlations between pH values and the acidic neutral basic adjectives will be different at temperatures other than 25 degrees C. For example, the Check Your Learning exercise accompanying example 14. One showed the hydronium molarity of pure water at 80 degrees C is 49 times 10⁻7 m, which corresponds to pH and pOH values of pH equals minus log H 3O plus equals minus log 4, 9 times 10⁻7 equals 6, 31. pOH equals minus log O minus equals minus log 4, 9 times 10⁻7 equals 6, 31. At this temperature, then, neutral solutions exhibit pH equals pOH equals 631. Acidic solutions exhibit pH less than 631 and pOH greater than 631, whereas basic solutions exhibit pH greater than 631 and pOH less than 631. This distinction can be important when studying certain processes that occur at other temperatures, such as enzyme reactions in warm-blooded organisms at a temperature around 3640 degrees C. Unless otherwise noted, references to pH values are presumed to be those at 25 degrees C, Table 14. 1. Summary of relations for acidic, basic, and neutral solutions. Classification relative ion concentrations, pH at 25 C. Acidic H3O+, O-BH7. Neutral H3O+, equals O-BH equals 7. Basic H3O+, O-BH7. Table 14. 1. Figure 14. 2 shows the relationships between H3O+, O-, pH, and pOH for solutions classified as acidic, basic, and neutral. A table is provided with 5 columns. The first column is labeled left bracket H subscript 3O superscript plus right bracket M. Powers of 10 are listed in the column beginning at 10 superscript 1, including 10 superscript 0 or 1, 10 superscript negative 1, decreasing by single powers of 10 to 10 superscript negative 15. The second column is labeled left bracket OH superscript negative right bracket M. Powers of 10 are listed in the column beginning at 10 superscript negative 15, increasing by single powers of 10 to including 10 superscript 0 or 1 and 10 superscript 1. The third column is labeled pH. Values listed in this column are integers beginning at -1, increasing by 1s up to 14. The fourth column is labeled pOH. Values in this column are integers beginning at 15, decreasing by 1s up to -1. The fifth column is labeled sample solution. A vertical line at the left of the column has tick marks corresponding to each pH level in the table. Substances are listed next to this line segment, with line segments connecting them to the line to show approximate pH and pOH values. 1-MHCl is listed at a pH of 0. Gastric juices are listed at a pH of about 1.5. Lime juice is listed at a pH of about 2, followed by 1-MCH subscript 3CO subscript 2H, followed by stomach acid at a pH value of nearly 3. Wine is listed around 3.5. Coffee is listed just past 5. Pure water is listed at a pH of 7. Pure blood is just beyond 7. Milk of magnesia is listed just past a pH of 10. 5. Household ammonia is listed just before a pH of 12. 1-MN, a OH is listed at a pH of 0. To the right of this labeled arrow is an arrow that points up and down through the height of the column. A beige strip passes through the table and to this double-headed arrow at pH 7. To the left of the double-headed arrow in this beige strip is the label neutral. A narrow beige strip runs through the arrow. Just above and below this region, the arrow is purple. It gradually turns to a bright red as it extends upward. At the top of the arrow, near the head of the arrow, is the label acidic. Similarly, the lower region changes color from purple to blue, moving to the bottom of the column. The head at this end of the arrow is labeled basic. Figure 14. 2. The pH and pOH scales represent concentrations of H3O+ and O-, respectively. The pH and pOH values of some common substances at 25 degrees C are shown in this chart. Example 14. 4. Calculation of pH from H3O+. What is the pH of stomach acid? a solution of HCl with a hydronium ion concentration of 1-2 times 10-3 m. Solution: pH equals minus log H 3O plus equals minus log 1 2 times 10-3 equals minus 2 92 equals 2 92. The use of logarithms is explained in Appendix B. When taking the log of a value, keep as many decimal places in the result as there are significant figures in the value. Check your learning. Water exposed to air contains carbonic acid, H2CO3, due to the reaction between carbon dioxide and water. CO2, letter 1D44, letter 1D45E, plus H2O, letter 1D459 H2CO, 3, letter 1D44, letter 1D45E. Air-saturated water has a hydronium ion concentration caused by the dissolved CO2 of 2 times 10-6 m, about 20 times larger than that of pure water. Calculate the pH of the solution at 25 degrees C. Answer: 570. Example 14. 5. Calculation of hydronium ion concentration from pH. Calculate the hydronium ion concentration of blood, the pH of which is 7.3. Solution: pH equals minus log H 3O plus equals 7, 3. Log H 3O plus equals minus 7, 3. H3O plus equals 10-7, 3 or H3O plus equals antilog of minus 7, 3. H3O plus equals 5 times 10-8 letter 1D440. On a calculator, take the antilog or the inverse log of minus 7, 3 or calculate 10-7, 3. Check your learning. Calculate the hydronium ion concentration of a solution with a pH of minus 1. 7. Answer: 12 m. How sciences interconnect. Environmental science. Normal rainwater has a pH between 5 and 6 due to the presence of dissolved CO2, which forms carbonic acid. H2O, letter 1D459, plus CO2, letter 1D454 H2CO 3, letter 1D44, letter 1D45E. H2CO 3, letter 1D44, letter 1D45E H plus, letter 1D44, letter 1D45E, plus HCO 3 minus, letter 1D44, letter 1D45E. Acid rain is rainwater that has a pH of less than 5, due to a variety of nonmetal oxides, including CO2, SO2, SO3, NO, and NO2 being dissolved in the water and reacting with it to form not only carbonic acid, but sulfuric acid and nitric acid. The formation and subsequent ionization of sulfuric acid are shown here. H2O, letter 1D459, plus SO3, letter 1D454 H2SO4, letter 1D44, letter 1D45E. H2SO4, letter 1D44, letter 1D45E H plus, letter 1D44, letter 1D45E, plus HSO4 minus, letter 1D44, letter 1D45E. Carbon dioxide is naturally present in the atmosphere because most organisms produce it as a waste product of metabolism. Carbon dioxide is also formed when fires release carbon stored in vegetation or fossil fuels. Sulfur trioxide in the atmosphere is naturally produced by volcanic activity, but it also originates from burning fossil fuels, which have traces of sulfur, and from the process of roasting ores of metal sulfides in metal refining processes. Oxides of nitrogen are formed in internal combustion engines, where the high temperatures make it possible for the nitrogen and oxygen in air to chemically combine. Acid rain is a particular problem in industrial areas, where the products of combustion and smelting are released into the air without being stripped of sulfur and nitrogen oxides. In North America and Europe until the 1980s, it was responsible for the destruction of forests and freshwater lakes, when the acidity of the rain actually killed trees, damaged soil, and made lakes uninhabitable for all but the most acid-tolerant species. Acid rain also corrodes statuary and building facades that are made of marble and limestone, figure 14. 3. Regulations limiting the amount of sulfur and nitrogen oxides that can be released into the atmosphere by industry and automobiles have reduced the severity of acid damage to both natural and man-made environments in North America and Europe. It is now a growing problem in industrial areas of China and India. For further information on acid rain, visit this website hosted by the U.S. Environmental Protection Agency. 2 photos are shown. Photograph on the left shows the upper portion of trees against a bright blue sky. The tops of several trees at the center of the photograph have bare branches and appear to be dead. Image B shows a statue of a man that appears to from the Revolutionary War era in either marble or limestone. Figure 14. 3. A. Acid rain makes trees more susceptible to drought and insect infestation and depletes nutrients in the soil. B. It also corrodes statues that are carved from marble or limestone. Credit, a modification of work by Chris M. Morris. Credit B. Modification of work by Eden, Janine, and Jim /Flickr. Example 14. 6. Calculation of pOH. What are the pOH and the pH of a 0? 125 m solution of potassium hydroxide, KOH. Solution. Potassium hydroxide is a highly soluble ionic compound and completely dissociates when dissolved in dilute solution, yielding O- equals 0. 125 m, pOH equals minus log O minus equals minus log 0. 125 equals minus 1. 903 equals 1. 903. The pH can be found from the pOH. pH plus PO equals 14. pH equals 14. 0, 0 minus PO equals 14. 0, 0 minus 1. 903 equals 12. 10. Check your learning. The hydronium ion concentration of vinegar is approximately 4 times 10 minus 3 m. What are the corresponding values of pOH and pH? Answer. pOH equals 11.6, pH equals 2.4. The acidity of a solution is typically assessed experimentally by measurement of its pH. The pOH of a solution is not usually measured, as it is easily calculated from an experimentally determined pH value. The pH of a solution can be directly measured using a pH meter, figure 14. 4. This figure contains 2 images. The first, image A, is of an analytical digital pH meter on a laboratory counter. The second, image B, is of a portable hand-held digital pH meter. Figure 14. 4a. A research-grade pH meter used in a laboratory can have a resolution of 0. 1 pH units, an accuracy of plus or minus 0. 2 pH units, and may cost in excess of $1,000. B. A portable pH meter has lower resolution, 0. 1 pH units, lower accuracy, plus or minus 0.2 pH units, and a far lower price tag. Credit B. Modification of work by Jacopo Werther. The pH of a solution may also be visually estimated using colored indicators. Figure 14. 5. The acid-base equilibria that enable use of these indicator dyes for pH measurements are described in a later section of this chapter. This figure contains 2 images. The first shows a variety of colors of solutions in labeled beakers. A red solution in a beaker is labeled 010 mHCl, an orange solution is labeled 010 mCH, subscript 3COOH. A yellow-orange solution is labeled 01 mNH, subscript 4Cl. A yellow solution is labeled deionized water. A second solution beaker is labeled 010 mKCl. A green solution is labeled 010 m-aniline. A blue solution is labeled 010 mNH, subscript 4Cl, a Q. A final beaker containing a dark blue solution is labeled 010 mN, a OH. Image B shows p-hydrian paper that is used for measuring pH in the range of pH from 1 to 12. The color scale for identifying pH based on color is shown along with several of the test strips used to evaluate pH. Figure 14. 5a. A solution containing a dye mixture, called universal indicator, takes on different colors depending upon its pH. B. Convenient test strips, called pH paper, contain embedded indicator dyes that yield pH-dependent color changes on contact with aqueous solutions. Credit, modification of work by Sahar Atwa. Learning objectives. By the end of this section, you will be able to assess the relative strengths of acids and bases according to their ionization constants, rationalize trends in acid, base strength in relation to molecular structure, carry out equilibrium calculations for weak acid, base systems, acid and base ionization constants. The relative strength of an acid or base is the extent to which it ionizes when dissolved in water. If the ionization reaction is essentially complete, the acid or base is termed strong. If relatively little ionization occurs, the acid or base is weak. As will be evident throughout the remainder of this chapter, there are many more weak acids and bases than strong ones. The most common strong acids and bases are listed in Figure 14. 6. This table has 7 rows and 2 columns. The first row is a header row, and it labels each column 6 strong acids and 6 strong bases. Under the 6 strong acids column are the following: HClO subscript 4-perchloric acid, HCl hydrochloric acid, HBr hydrobromic acid, HI hydriodic acid, HNO subscript 3 nitric acid, H subscript 2 SO subscript 4 sulfuric acid. Under the 6 strong bases column are the following: LiOH lithium hydroxide, NaOH sodium hydroxide, KOH potassium hydroxide, COOH subscript 2 calcium hydroxide, SROH subscript 2 strontium hydroxide, BOOH subscript 2 barium hydroxide. Figure 14. 6. Some of the common strong acids and bases are listed here. The relative strengths of acids may be quantified by measuring their equilibrium constants in aqueous solutions. In solutions of the same concentration, stronger acids ionize to a greater extent, and so yield higher concentrations of hydronium ions than do weaker acids. The equilibrium constant for an acid is called the acid ionization constant, Ka, for the reaction of an acid Ha letter 1d44 letter 1d45e, plus H2O, letter 1d459, H3O plus letter 1d44 letter 1d45e, plus a minus, letter 1d44 letter 1d45e. The acid ionization constant is written, letter 1d43e, A equals H3O plus a minus Ha, where the concentrations are those at equilibrium. Although water is a reactant in the reaction, it is the solvent as well, so we do not include H2O in the equation. The larger the Ka of an acid, the larger the concentration of H3O+, and a minus relative to the concentration of the non-ionized acid, Ha, in an equilibrium mixture, and the stronger the acid. An acid is classified as strong when it undergoes complete ionization, in which case the concentration of Ha is 0, and the acid ionization constant is immeasurably large, Ka approximately infinity. Acids that are partially ionized are called weak, and their acid ionization constants may be experimentally measured. A table of ionization constants for weak acids is provided in Appendix H. To illustrate this idea, 3 acid ionization equations and Ka values are shown below. The ionization constants increase from first to last of the listed equations, indicating the relative acid strength increases in the order CH3-CoH, HNO2, HSO4-, CH3-CoH, letter 1d44 letter 1d45e, plus H2O letter 1d459H, 3O+, letter 1d44 letter 1d45e plus, CH3-Co2-, letter 1d44 letter 1d45e letter 1d43e, equals 1. 8 times 10 minus 5, HNO2, letter 1d44 letter 1d45e, plus H2O, letter 1d459H, 3O+, letter 1d44 letter 1d45e, plus No2 minus, letter 1d44 letter 1d45e letter 1d43e, equals 4. 6 times 10 minus 4, HSO 4 minus, letter 1d44 letter 1d45e, plus H2O letter 1d44 letter 1d45e H, 3O plus, letter 1d44 letter 1d45e, plus So 42 minus letter 1d44 letter 1d45e, letter 1d43e, equals 1. 2 times 10 minus 2. Another measure of the strength of an acid is its percent ionization. The percent ionization of a weak acid is defined in terms of the composition of an equilibrium mixture. Percent ionization equals H3O plus Ka0 times 100, where the numerator is equivalent to the concentration of the acid's conjugate base. Per stoichiometry, a minus equals H3O plus. Unlike the Ka value, the percent ionization of a weak acid varies with the initial concentration of acid, typically decreasing as concentration increases. Equilibrium calculations of the sort described later in this chapter can be used to confirm this behavior. Example 14, 7. Calculation of percent ionization from pH. Calculate the percent ionization of a 0-125 m solution of nitrous acid, a weak acid, with a pH of 2.9. Solution. The percent ionization for an acid is H3O plus HNO20 times 100. Converting the provided pH to hydronium ion molarity yields. H3O plus equals 10 minus 2. 0.9 equals 0. 81 m. Substituting this value and the provided initial acid concentration into the percent ionization equation gives 8 1 times 10 minus 30. 125 times 100 equals 6. 5%. Recall the provided pH value of 2. 9 is logarithmic, and so it contains just 2 significant digits, limiting the certainty of the computed percent ionization. Check your learning. Calculate the percent ionization of a 0.10 m solution of acetic acid with a pH of 289. Answer: 13% ionized. Link to learning. View the simulation of strong and weak acids and bases at the molecular level. Just as for acids, the relative strength of a base is reflected in the magnitude of its base ionization constant, Kb, in aqueous solutions. In solutions of the same concentration, stronger bases ionize to a greater extent, and so yield higher hydroxide ion concentrations than do weaker bases. A stronger base has a larger ionization constant than does a weaker base. For the reaction of a base B, BHO, HB+, letter 1d44, letter 1d45e, plus O minus, letter 1d44, letter 1d45e. The ionization constant is written as letter 1d43b equals HB plus O minus B. Inspection of the data for 3 weak bases presented below shows the base strength increases in the order No 2 minus CH to CO, 2 minus NH3. No 2 minus, letter 1d44, letter 1d45e, plus H2O, letter 1d459 HNO, 2, letter 1d44, letter 1d45e, plus O minus, letter 1d44, letter 1d45e, CH, 3 CO 2 minus, letter 1d44, letter 1d45e, plus H2O, letter 1d459 CH, 3 CO 2. H, letter 1d44, letter 1d45e, plus O minus, letter 1d44, letter 1d45e NH, 3, letter 1d44, letter 1d45e plus H2O. Letter 1d459 NH, 4 plus letter 1d44, letter 1d45e, plus O minus, letter 1d44, letter 1d45e, letter 1d43b, letter 1d43b, letter 1d43b equals 2. 17 times 10 minus 115, 6 times 10 minus 101, 8 times 10 minus 5. A table of ionization constants for weak bases appears in Appendix I. As for acids, the relative strength of a base is also reflected in its percent ionization, computed as percent ionization equals O minus letter 1d45 to letter 1d45e slash B0 times 100%, but will vary depending on the base ionization constant and the initial concentration of the solution. Relative strengths of conjugate acid-base pairs. Bronsted-Lurey acid-base chemistry is the transfer of protons. Thus, logic suggests a relation between the relative strengths of conjugate acid-base pairs. The strength of an acid or base is quantified in its ionization constant, Ka or Kb, which represents the extent of the acid or base ionization reaction. For the conjugate acid-base pair Ha/A-, ionization equilibrium equations and ionization constant expressions are Ha letter 1d44 letter 1d45e plus H2O letter 1d459, H3O plus letter 1d44 letter 1d45e plus a minus letter 1d44 letter 1d45e letter 1d43e equals H3O plus a minus Ha. A minus letter 1d44 letter 1d45e plus H2O letter 1d4590 minus letter 1d44 letter 1d45e plus Ha letter 1d44 letter 1d45e letter 1d43b equals Ha a minus. Adding these two chemical equations yields the equation for the autoionization for water. Ha letter 1d44 letter 1d45e plus H2O letter 1d459 plus a minus letter 1d44 letter 1d45e plus H2O letter 1d459H 3O plus letter 1d44 letter 1d45e plus a minus letter 1d44 letter 1d45e plus O minus letter 1d44 letter 1d45e plus Ha letter 1d44 letter 1d45e. 2H2O letter 1d459 H3O plus letter 1d44 letter 1d45e plus O minus letter 1d44 letter 1d45e. As discussed in another chapter on equilibrium, the equilibrium constant for a summed reaction is equal to the mathematical product of the equilibrium constants for the added reactions. And so, letter 1d43, a times letter 1d43b equals h, 3o plus a minus ha times ha minus a minus equals h, 3o plus o minus equals letter 1d43w. This equation states the relation between ionization constants for any conjugate acid-base pair. Namely, their mathematical product is equal to the ion product of water, Kw. By rearranging this equation, a reciprocal relation between the strengths of a conjugate acid-base pair becomes evident. Letter 1d43e equals letter 1d43w slash letter 1d43e bor, letter 1d43b equals letter 1d43w slash letter 1d43e. The inverse proportional relation between Ka and Kb means the stronger the acid or base, the weaker its conjugate partner. Figure 14.7 illustrates this relation for several conjugate acid-base pairs. The diagram shows two horizontal bars. The first, labeled relative acid strength, at the top is red on the left and gradually changes to purple on the right. The red end at the left is labeled stronger acids. The purple end at the right is labeled weaker acids. Just outside the bar to the lower left is the label K subscript A. The bar is marked off in increments with a specific acid listed above each increment. The first mark is at 10 with H subscript 30 superscript positive sign. The second is 10 raised to the negative 2 with HClO subscript 2. The third is 10 raised to the negative 4 with H. F. The fourth is 10 raised to the negative 6 with H subscript 2 CO subscript 3. The fifth is 10 raised to a negative 8 with CH subscript 3 COOH. The sixth is 10 raised to the negative 10 with NH subscript 4 superscript positive sign. The seventh is 10 raised to a negative 12 with HPO subscript 4 superscript 2 negative sign. The eighth is 10 raised to the negative 14 with H subscript 2O. Similarly, the second bar, which is labeled relative conjugate base strength, is purple at the left end and gradually becomes blue at the right end. Outside the bar to the left is the label weaker bases. Outside the bar to the right is the label stronger bases. Below and to the left of the bar is the label K subscript B. The bar is similarly marked at increments with bases listed above each increment. The first is at 10 raised to the negative 14 with H subscript 2O above it. The second is 10 raised to the negative 12 ClO subscript 2 superscript negative sign. The third is 10 raised to the negative 10 with F superscript negative sign. The fourth is 10 raised to a negative 8 with HCO subscript 3 superscript negative sign. The fifth is 10 raised to the negative 6 with CH subscript 3 COO superscript negative sign. The sixth is 10 raised to the negative 4 with NH subscript 3. The seventh is 10 raised to the negative 2 with PO subscript 4 superscript 3 negative sign. The eighth is 10 with OH superscript negative sign. Figure 14. 7 relative strengths of several conjugate acid-base pairs are shown. This figure includes a table separated into a left half which is labeled acids and a right half labeled bases. A red arrow points up the left side, which is labeled increasing acid strength. Similarly, a blue arrow points downward along the right side, which is labeled increasing base strength. Names of acids and bases are listed next to each arrow toward the center of the table, followed by chemical formulas. Acids listed top to bottom are sulfuric acid, H subscript 2 SO subscript 4, hydrogen iodide, HI, hydrogen bromide, HBr, hydrogen chloride, HCl, nitric acid, HNO subscript 3, hydronium ion, in pink text, H subscript 3O superscript plus, hydrogen sulfate ion, HSO subscript 4 superscript negative, phosphoric acid, H subscript 3PO subscript 4, hydrogen fluoride, HF, nitrous acid, HNO subscript 2, acetic acid, CH subscript 3CO subscript 2H, carbonic acid H subscript 2CO subscript 3, hydrogen sulfide, H subscript 2S, ammonium ion, NH subscript 4 superscript plus, hydrogen cyanide, HCN, hydrogen carbonate ion, HCO subscript 3 superscript negative, water, shaded in beige H subscript 2O, hydrogen sulfide ion, HS superscript negative, ethanol, C subscript 2H subscript 50H ammonia. NH subscript 3, hydrogen, H subscript 2, methane, and CH subscript 4. The acids at the top of the listing from sulfuric acid through nitric acid are grouped with a bracket to the right labeled undergo complete acid ionization in water. Similarly, the acids at the bottom from hydrogen sulfide ion through methane are grouped with a bracket and labeled do not undergo acid ionization in water. The right half of the figure lists bases and formulas. From top to bottom, the bases listed are hydrogen sulfate ion, HSO subscript 4 superscript negative, iodide ion, I superscript negative, bromide ion, Br superscript negative, chloride ion, Cl superscript negative, nitrate ion, NO subscript 3 superscript negative, water shaded in beige, H subscript 2O sulfate ion, SO subscript 4 superscript 2 negative, dihydrogen phosphate ion, H subscript 2PO subscript 4 superscript negative, fluoride ion, F superscript negative, nitrite ion, NO subscript 2 superscript negative, acetate ion, CH subscript 3CO subscript 2 superscript negative, hydrogen carbonate ion, HCO subscript 3 superscript negative, hydrogen sulfide ion, HS superscript negative, ammonia, NH subscript 3, cyanide ion, CN superscript negative, carbonate ion, CO subscript 3 superscript 2 negative, hydroxide ion in blue, OH superscript negative, sulfide ion, S superscript 2 negative, ethoxide ion, C subscript 2H subscript 50 superscript negative, amide ion NH subscript 2 superscript negative, hydride ion, H superscript negative, and methide ion CH subscript 3 superscript negative. The bases at the top, from perchlorate ion through nitrate ion, are grouped with a bracket which is labeled, do not undergo base ionization in water. Similarly, the lower 5 in the listing, from sulfide ion through methide ion, are grouped and labeled, undergo complete base ionization in water. Figure 14. 8. This figure shows strengths of conjugate acid-base pairs relative to the strength of water as the reference substance. The listing of conjugate acid-base pairs shown in Figure 14. 8 is arranged to show the relative strength of each species as compared with water, whose entries are highlighted in each of the table's columns. In the acid column, those species listed below water are weaker acids than water. These species do not undergo acid ionization in water. They are not Bronsted-Lowry acids. All the species listed above water are stronger acids, transferring protons to water to some extent when dissolved in an aqueous solution to generate hydronium ions. Species above water but below hydronium ion are weak acids, undergoing partial acid ionization, whereas those above hydronium ion are strong acids that are completely ionized in aqueous solution. If all these strong acids are completely ionized in water, why does the column indicate they vary in strength, with nitric acid being the weakest and perchloric acid the strongest? Notice that the sole acid species present in an aqueous solution of any strong acid is H3O+, AC, meaning that hydronium ion is the strongest acid that may exist in water. Any stronger acid will react completely with water to generate hydronium ions. This limit on the acid strength of solutes in a solution is called a leveling effect. To measure the differences in acid strength for strong acids, the acids must be dissolved in a solvent that is less basic than water. In such solvents, the acids will be weak, and so any differences in the extent of their ionization can be determined. For example, the binary hydrogen halides HCl, HBr, and HI are strong acids in water but weak acids in ethanol, strength increasing HCl, HBr, HI. The right column of Figure 14. 8 lists a number of substances in order of increasing base strength from top to bottom. Following the same logic as for the left column, species listed above water are weaker bases, and so they don't undergo base ionization when dissolved in water. Species listed between water and its conjugate base, hydroxide ion, are weak bases that partially ionize. Species listed below hydroxide ion are strong bases that completely ionize in water to yield hydroxide ions, I. E. They are leveled to hydroxide. A comparison of the acid and base columns in this table supports the reciprocal relation between the strengths of conjugate acid-base pairs. For example, the conjugate bases of the strong acids, top of table, are all of negligible strength. A strong acid exhibits an immeasurably large Ka, and so its conjugate base will exhibit a Kb that is essentially zero. Strong acid, letter 1d43, of approximately infinity conjugate base. Letter 1d43b equals letter 1d43w slash letter 1d43, a equals letter 1d43w slash infinity approximately 0. A similar approach can be used to support the observation that conjugate acids of strong bases, Kb approximately infinity, are of negligible strength, Ka approximately 0. Example 14. 8 calculating ionization constants for conjugate acid-base pairs. Use the Kb for the nitrite ion, NO2-, to calculate the Ka for its conjugate acid. Solution Kb for NO2- is given in this section as 217 times 10⁻11. The conjugate acid of NO2- is HNO2. Ka for HNO2 can be calculated using the relationship letter 1d43 a times letter 1d43b equals 1. 0 times 10⁻14 equals letter 1d43w. Solving for Ka yields letter 1d43a, a equals letter 1d43w, letter 1d43b equals 1. 0 times 10⁻142. 17 times 10⁻11 equals 4. 6 times 10⁻4. This answer can be verified by finding the Ka for HNO2 in Appendix H. Check your learning. Determine the relative acid strengths of NH4+ and HCN by comparing their ionization constants. The ionization constant of HCN is given in Appendix H as 4. 9 times 10⁻10. The ionization constant of NH4+ is not listed, but the ionization constant of its conjugate base, NH3, is listed as 1/8 times 10⁻5. Answer: NH4+ is the slightly stronger acid. Ka for NH4+ equals 5/6 times 10⁻10. Acid-base equilibrium calculations. The chapter on chemical equilibria introduced several types of equilibrium calculations and the various mathematical strategies that are helpful in performing them. These strategies are generally useful for equilibrium systems regardless of chemical reaction class, and so they may be effectively applied to acid-base equilibrium problems. This section presents several example exercises involving equilibrium calculations for acid-base systems. This image shows 2 bottles containing clear colorless solutions. Each bottle contains a single pH indicator strip. The strip in the bottle on the left is red, and a similar red strip is placed on a filter paper circle in front of the bottle on surface on which the bottles are resting. Similarly, the second bottle on the right contains an orange strip, and an orange strip is placed in front of it on a filter paper circle. Between the 2 bottles is a pack of p-hydrogen papers with a pH color scale on its cover. This photo shows 2 glass containers filled with a transparent liquid. In between the containers is a pH strip indicator guide. There are pH strips placed in front of each glass container. The liquid in the container on the left appears to have a pH of 10 or 11. The liquid in the container on the right appears to have a pH of about 13 or 14. Example 14. 9 Determination of Ka from equilibrium concentrations. Acetic acid is the principal ingredient in vinegar, figure 14. 9. That provides its sour taste. At equilibrium, a solution contains CH3CO2H equals 0. 787 m and H3O plus equals CH3CO2 minus equals 0. 118 m. What is the value of Ka for acetic acid? An image shows the label of a bottle of distilled white vinegar. The label states that the contents have been reduced with water to 5% acidity. Figure 14. 9 Vinegar contains acetic acid, a weak acid. Credit: modification of work by Homespot HQ/Flickr. Solution: the relevant equilibrium equation and its equilibrium constant expression are shown below. Substitution of the provided equilibrium concentrations permits a straightforward calculation of the Ka for acetic acid. CH3COATH, letter 1d44, letter 1d45e, plus H2O, letter 1D459H3O plus, letter 1D44, letter 1D45E plus, CH3CO2 minus, letter 1D44, letter 1D45E, letter 1D43E, A equals H3O plus CH3CO2 minus CH3 H equals 0. 0, 0, 1, 1, 8, 0. 0, 0, 1, 1, 8, 0. 0, 7, 8, 7 equals 1. 77 times 10 minus 5 check, you're learning the HSO4 minus ion, weak acid used in some household cleansers. HSO4 minus, letter 1D44, letter 1D45E, plus H2O, letter 1D459H3O plus, letter 1D44, letter 1D45E, plus so 42 minus letter 1D44, letter 1D45E. What is the acid ionization constant for this weak acid if an equilibrium mixture has the following composition? H3O plus equals 0, 27M, HSO4 minus equals 0, 29M, and so 42 minus equals 0. Answer. Ca for HSO4 minus equals 1 2 times 10 minus 2, example 14. 10 determination of Kb from equilibrium concentrations, caffeine, C8H10 and 4O2 is a weak base. What is the value of Kb for caffeine if a solution at equilibrium has C8H10 and 4O2 equals 0? 50 m, C8H10 and 4O2H plus equals 5. 0 times 10 minus 3m, and O minus equals 25 times 10 minus 3m. Solution, the relevant equilibrium equation, and its equilibrium constant expression are shown below. Substitution of the provided equilibrium concentrations permits a straightforward calculation of the Kb for caffeine. C8H10 and 4O2, letter 1D44, letter 1D45E, plus H2O, letter 1D459C, 8H10 and 4OH plus, letter 1D44, letter 1D45E, plus O minus letter 1D44, letter 1D45E, letter 1D43B equals C, 8H10 and 4OH plus O minus C, 8H10 and 4O2 equals 5. 0 times 10 minus 3, 2. 5 times 10 minus 3, 0. 0, 50 equals 2. 5 times 10 minus 4, check your learning. What is the equilibrium constant for the ionization of the HPO 42 minus ion? A weak base HPO 42 minus, letter 1D44, letter 1D45E, plus H2O, letter 1D459, H2PO 4 minus, letter 1D44, letter 1D45E, plus O minus, letter 1D44, letter 1D45E, if the composition of an equilibrium mixture is as follows. O minus equals 1 3 times 10 minus 6m, H2PO 4 minus equals 0. 42m, and HPO 42 minus equals 0. 341m. Answer. Kb for HPO 42 minus equals 1. 6 times 10 minus 7, example 14. 11 determination of Ca or Kb from pH, the pH of a 0. 516m solution of nitrous acid, HNO2, is 234. What is its Ca? HNO2, letter 1D44, letter 1D45E, plus H2O, letter 1D459H3O plus, letter 1D44, letter 1D45E, plus No2 minus, letter 1D44, letter 1D45E. Solution, the nitrous acid concentration provided is a formal concentration, one that does not account for any chemical equilibria that may be established in solution. Such concentrations are treated as initial values for equilibrium calculations using the ice table approach. Notice the initial value of hydronium ion is listed as approximately 0 because a small concentration of H3O+ is present, 1 times 10 minus 7m, due to the autoprotolysis of water. In many cases, such as all the ones presented in this chapter, this concentration is much less than that generated by ionization of the acid or base in question and may be neglected. The pH provided is a logarithmic measure of the hydronium ion concentration resulting from the acid ionization of the nitrous acid, and so it represents an equilibrium value for the ice table. H3O plus equals 10 minus 2. 34 equals 0. 46m, the ice table for this system, is then this table has 2 main columns and 4 rows. The first row for the first column does not have a heading and then has the following in the first column. Initial concentration, M, change M, equilibrium concentration, M. The second column has the header of HNO subscript 2, plus sine H subscript 2 O equilibrium sine H subscript 3 O superscript positive sine plus sine NO subscript 2 superscript negative sine. Under the second column is a subgroup of 4 columns and 3 rows. The first column has the following: 0, 5, 16, negative 0. 46, 0, 4, 70. The second column is blank in all 3 rows. The third column has the following: approximately 0, positive 0, 46, 0, 46. The fourth column has the following: 0, positive 0, 46, 0, 46. Finally, calculate the value of the equilibrium constant using the data in the table. Letter 1D43 A equals H3 O plus no 2 minus HNO 2 equals 0. 0, 0, 46, 0, 0, 0, 46, 0, 0, 470 equals 4. 6 times 10 minus 4 check your learning. The pH of a solution of household ammonia, a 0. 950 m solution of NH3 is 11, 612. What is Kb for NH3? Answer: Kb equals 18 times 10 minus 5 example 14. 12 Calculating equilibrium concentrations in a weak acid solution. Formic acid, HCO2H, is one irritant that causes the body's reaction to some ant bites and stings, figure 14. 10. A photograph is shown of a large black ant on the end of a human finger, figure 14. 10. The pain of some ant bites and stings is caused by formic acid. Credit: John Tan. What is the concentration of hydronium ion and the pH of a 0,534 m solution of formic acid? HCO2H, letter 1D44, letter 1D45E, plus H2O, letter 1D459H, 3O plus, letter 1D44, letter 1D45E, plus HCO2 minus, letter 1D44, letter 1D45E, letter 1D43E, A equals 1. 8 times 10 minus 4 solution. The ice table for this system is this table has 2 main columns and 4 rows. The first row for the first column does not have a heading and then has the following in the first column: initial concentration, M, change M, equilibrium concentration, M. The second column has the header of HCO subscript 2H plus sine H subscript 2O equilibrium arrow H subscript 3O superscript positive sine. Under the second column is a subgroup of 4 columns and 3 rows. The first column has the following: 0, 534, blank, 0, 534 minus X. The second column is blank in all 3 rows. The third column has the following: approximately 0, positive X, X. The fourth column has the following: 0, positive X, X. Substituting the equilibrium concentration terms into the Ka expression gives letter 1D43 A equals 1. 8 times 10 minus 4 equals H3, O plus HCO, 2 minus HCO2H, equals letter 1D465. Letter 1D4650. 534 minus letter 1D465 equals 1. 8 times 10 minus 4. The relatively large initial concentration and small equilibrium constant permits the simplifying assumption that X will be much lesser than 0. 534, and so the equation becomes letter 1D43A equals 1. 8 times 10 minus 4 equals letter 1D465 20. 534, solving the equation for X yields letter 1D465 2 equals 0. 534 times 1. 8 times 10 minus 4 equals 9. 6 times 10 minus 5, letter 1D465 equals 9. 6 times 10 minus 5 square equals 9. 8 times 10 minus 3, letter 1D440, to check the assumption that X is small compared to 0. 534, its relative magnitude can be estimated, X 0. 534 equals 9. 8 times 10 minus 30. 534 equals 1. 8 times 10 minus 2, 1. 8% of 0, 534. Because X is less than 5% of the initial concentration, the assumption is valid. As defined in the ice table, X is equal to the equilibrium concentration of hydronium ion. Letter 1D465 equals H, 3O plus equals 0. 98 m. Finally, the pH is calculated to be pH equals minus log H, 3O plus equals minus log 0. 0098 equals 2. 1. Check your learning. Only a small fraction of a weak acid, ionizes in aqueous solution. What is the percent ionization of a 0-100 m solution of acetic acid, CH3-CoH? CH3-CoH, letter 1d44, letter 1d45e, plus H2, letter 1d459H, 3O plus, letter 1d44, letter 1d45e plus, CH3-Co2 minus, letter 1d44, letter 1d45e, letter 1d43e, equals 1. 8 times 10 minus 5 answer. Percent ionization equals 13%. Example 14. 13. Calculating equilibrium concentrations in a weak base solution. Find the concentration of hydroxide ion, the pOH, and the pH of a 0.25 m solution of trimethylamine, a weak base. CH33N, letter 1d44, letter 1d45e, plus H2, letter 1d459. CH33NH plus, letter 1d44, letter 1d45e, plus O minus, letter 1d44, letter 1d45e, letter 1d43b, equals 6. 3 times 10 minus 5 solution. The ICE table for this system is this table has 2 main columns and 4 rows. The first row for the first column does not have a heading and then has the following in the first column: initial concentration, M, change M, equilibrium concentration, M. The second column has the header of CH subscript 3, subscript 3N plus sign H subscript 2 O equilibrium arrow, CH subscript 3, subscript 3NH superscript positive sign plus sign OH superscript positive sign. Under the second column is a subgroup of 4 columns and 3 rows. The first column has the following: 0.25, negative X, 0.25 plus sign negative X. The second column is blank in all 3 rows. The third column has the following: 0x, 0 plus x. The fourth column has the following: approximately 0x and approximately 0 plus x. Substituting the equilibrium concentration terms into the Kb expression gives letter 1d43b equals CH3, 3NH plus O minus, CH3, 3N equals letter 1d465, letter 1d465, 0. 25 minus letter 1d465 equals 6. 3 times 10 minus 5, assuming x 0.25 and solving for x yields. This value is less than 5% of the initial concentration, 0.25, so the assumption is justified. As defined in the ICE table, x is equal to the equilibrium concentration of hydroxide ion. O minus equals tilde 0 plus letter 1d465 equals letter 1d465 equals 4. 0 times 10 minus 3 letter 1d440 equals 4. 0 times 10 minus 3 letter 1d440, the pOH is calculated to be pOH equals minus log 4. 0 times 10 minus 3 equals 2. 40 using the relation introduced in the previous section of this chapter. pH plus pOH equals P letter 1d43W equals 14. Permits the computation of pH. pH equals 14. 0, 0 minus PO equals 14. 0, 0 minus 2. 40 equals 11. 60. Check your learning. Calculate the hydroxide ion concentration and the percent ionization of a 0.325 m solution of ammonia, a weak base with a Kb of 1. 76 times 10 minus 5. Answer: 756 times 10 minus 4 m, 233% in some cases, the strength of the weak acid or base, and its formal initial concentration result in an appreciable ionization. Though the ICE strategy remains effective for these systems, the algebra is a bit more involved because the simplifying assumption that X is negligible cannot be made. Calculations of this sort are demonstrated in example 14. 14 below. Example 14. 14. Calculating equilibrium concentrations without simplifying assumptions. Sodium bisulfate, NaHSO4, is used in some household cleansers as a source of the HSO4- ion, a weak acid. What is the pH of a 0.50 m solution of HSO4-? HSO4-, letter 1d44, letter 1d45e, plus H2, letter 1d459, H3O plus letter 1d44, letter 1d45e, plus SO42-, letter 1d44, letter 1d45e, letter 1d43e, equals 1. 2 times 10 minus 2 solution. The ICE table for this system is this table has 2 main columns and 4 rows. The first row for the first column does not have a heading and then has the following in the first column: initial concentration, M, change M, equilibrium M. The second column has the header of HSO subscript 4 superscript negative sign, plus sign H subscript 2O equilibrium sign H subscript 3O superscript positive sign, plus sign SO subscript 4 superscript 2 superscript negative sign. Under the second column is a subgroup of 4 columns and 3 rows. The first column has the following: 0, 50, negative x, 0, 50 minus x. The second column is blank for all 3 rows. The third column has the following: approximately 0, positive x, x. The fourth column has the following: 0, positive x, x. Substituting the equilibrium concentration terms into the Ka expression gives letter 1d43, A equals 1. 2 times 10 minus 2 equals H3, O plus O 42 minus HSO 4 minus equals letter 1d465. Letter 1d465, 0. 50 minus letter 1d465 if the assumption that x05 is made. Simplifying and solving the above equation yields 77m. This value of x is clearly not significantly less than 0. 50m. Rather, it is approximately 15% of the initial concentration. When we check the assumption, we calculate letter 1d465 HSO 4 minus I x0. 50 equals 7. 7 times 10 minus 20. 50 equals 0. 15%. Because the simplifying assumption is not valid for this system, the equilibrium constant expression is solved as follows. Letter 1d43, A equals 1. 2 times 10 minus 2 equals letter 1d465, letter 1d465, 0. 50 minus letter 1d465, rearranging this equation, yields 6. 0 times 10 minus 3 minus 1. 2 times 10 minus 2, letter 1d465, equals letter 1d465. 2. Writing the equation in quadratic form gives x2 plus 1. 2 times 10 minus 2, letter 1d465 minus 6. 0 times 10 minus 3 equals 0. Solving for the 2 roots of this quadratic equation results in a negative value that may be discarded as physically irrelevant and a positive value equal to x. As defined in the ICE table, x is equal to the hydronium concentration. Letter 1d465 equals H3O plus equals 0. H log HO log 0.72 equals 1. 14. Check your learning. Calculate the pH in a 0,10m solution of caffeine, a weak base. C8H10N4O2, letter 1d44, letter 1d45e, plus H2O, letter 1d459C, 8H10N4OH plus, letter 1d44, letter 1d45e, plus O minus letter 1d44, letter 1d45e, letter 1d43b equals 2. 5 times 10 minus 4 answer. pH 11. 16. Effect of molecular structure on acid-base strength, binary acids and bases in the absence of any leveling effect. The acid strength of binary compounds of hydrogen with nonmetals, A, increases as the HA bond strength decreases down a group in the periodic table. For group 17, the order of increasing acidity is HF, HCl, HBr, HI. Likewise, for group 16, the order of increasing acid strength is H2O, H2S, H2C, H2T. Across a row in the periodic table, the acid strength of binary hydrogen compounds increases with increasing electronegativity of the nonmetal atom, because the polarity of the HA bond increases. Thus, the order of increasing acidity, for removal of one proton, across the second row is CH4NH3H2OHF. Across the third row, it is CH4PH3H2SHCl, see figure 14. 11. This diagram has 2 rows and 4 columns. Red arrows point left across the bottom of the figure and down at the right side and are labeled increasing acid strength. Blue arrows point left across the bottom and up at the right side of the figure and are labeled increasing base strength. The first column is labeled 14 at the top and 2 white squares are beneath it. The first has the number 6 in the upper left corner, and the formula CH subscript 4 in the center, along with designation neither acid nor base. The second square contains the number 14 in the upper left corner, the formula CH subscript 4 at the center, and the designation neither acid nor base. The second column is labeled 15 at the top, and 2 blue squares are beneath it. The first has the number 7 in the upper left corner, and the formula NH subscript 3 in the center, along with the designation weak base and K subscript B equals 1. 8 times 10 superscript negative 5. The second square contains the number 15 in the upper left corner, the formula pH subscript 3 at the center, and the designation very weak base and K subscript B equals 4 times 10 superscript negative 28. The third column is labeled 16 at the top and 2 squares are beneath it. The first is shaded tan and has the number 8 in the upper left corner, and the formula H subscript 2O in the center, along with the designation neutral. The second square is shaded pink, contains the number 16 in the upper left corner, the formula H subscript 2S at the center, and the designation weak acid, and K subscript A equals 9. 5 times 10 superscript negative 8. The fourth column is labeled 17 at the top, and 2 squares are beneath it. The first is shaded pink, has the number 9 in the upper left corner, and the formula HF in the center, along with the designation weak acid, and K subscript A equals 6. 8 times 10 superscript negative 4. The second square is shaded a deeper pink, contains the number 17 in the upper left corner, the formula HCl at the center, and the designation strong acid. Figure 14. 11. The figure shows trends in the strengths of binary acids and bases. Ternary acids and bases, ternary compounds composed of hydrogen, oxygen, and some third element, E, may be structured as depicted in the image below. In these compounds, the central E atom is bonded to one or more O atoms, and at least one of the O atoms is also bonded to an H atom, corresponding to the general molecular formula EON. These compounds may be acidic, basic, or amphoteric depending on the properties of the central E atom. Examples of such compounds include sulfuric acid, O2S, O2, sulfurous acid, OS, O2, nitric acid, OTNO, perchloric acid, O3ClO, aluminum hydroxide, AlO3, calcium hydroxide, CaO2, and potassium hydroxide, KOH. A diagram is shown that includes a central atom designated with the letter E single bonds extend above, below, left, and right of the E. An O atom is bonded to the right of the E, and an arrow points to the bond labeling it, bond A. An H atom is single bonded to the right of the O atom. An arrow pointing to this bond connects it to the label, bond B. If the central atom, E, has a low electronegativity, its attraction for electrons is low. Little tendency exists for the central atom to form a strong covalent bond with the oxygen atom. And bond between the element and oxygen is more readily broken than bond B between oxygen and hydrogen. Hence, bond as ionic hydroxide ions are released to the solution, and the material behaves as a base. This is the case with Ca, O2, and KOH. Lower electronegativity is characteristic of the more metallic elements. Hence, the metallic elements form ionic hydroxides that are by definition basic compounds. If, on the other hand, the atom E has a relatively high electronegativity, it strongly attracts the electrons it shares with the oxygen atom, making bond a relatively strongly covalent. The oxygen-hydrogen bond, bond B, is thereby weakened because electrons are displaced toward E. Bond B is polar and readily releases hydrogen ions to the solution, so the material behaves as an acid. High electronegativities are characteristic of the more nonmetallic elements. Thus, nonmetallic elements form covalent compounds containing acidic -O groups that are called oxyacids. Increasing the oxidation number of the central atom, E also increases the acidity of an oxyacid, because this increases the attraction of E for the electrons it shares with oxygen and thereby weakens the OH bond. Sulfuric acid, H2SO4 or OSO, with a sulfur oxidation number of +6, is more acidic than sulfurous acid, H2SO3 or OS. O2, with a sulfur oxidation number of +4. Likewise, nitric acid, HNO3 or OTNO, N oxidation number +5, is more acidic than nitrous acid, HNO2 or ONOH, N oxidation number equals +3. In each of these pairs, the oxidation number of the central atom is larger for the stronger acid, figure 14. 12. A diagram is shown that includes 4 structural formulas for acids. A red, right-pointing arrow is placed beneath the structures which is labeled increasing acid strength. At the top left, the structure of nitrous acid is provided. It includes an H atom to which an O atom with 2 unshared electron pairs is connected with a single bond to the right. A single bond extends to the right and slightly below to an N atom with 1 unshared electron pair. A double bond extends up and to the right from this N atom to an O atom which has 2 unshared electron pairs. To the upper right is a structure for nitric acid. This structure differs from the previous structure in that the N atom is directly to the right of the first O atom, and a second O atom with 3 unshared electron pairs is connected with a single bond below, and to the right of the N atom, which has no unshared electron pairs. At the lower left, an O atom with 2 unshared electron pairs is double bonded to its right to an S atom with a single unshared electron pair. An O atom with 2 unshared electron pairs is bonded above, and an H atom is single bonded to this O atom. To the right of the S atom is a single bond to another O atom with 2 unshared electron pairs to which an H atom is single bonded. This structure is labeled sulfurous acid. A similar structure which is labeled sulfuric acid is placed in the lower right region of the figure. This structure differs in that an H atom is single bonded to the left of the first O atom, leaving it with 2 unshared electron pairs, and a fourth O atom with 2 unshared electron pairs is double bonded beneath the S atom, leaving it with no unshared electron pairs. Figure 14. 12. As the oxidation number of the central atom E increases, the acidity also increases. Hydroxy compounds of elements with intermediate electronegativities and relatively high oxidation numbers, for example, elements near the diagonal line separating the metals from the nonmetals in the periodic table, are usually amphoteric. This means that the hydroxy compounds act as acids when they react with strong bases and as bases when they react with strong acids. The amphoterism of aluminum hydroxide, which commonly exists as the hydrate Al, H2O3, O3, is reflected in its solubility in both strong acids and strong bases. In strong bases, the relatively insoluble hydrated aluminum hydroxide, Al H2O3, O3, is converted into the soluble ion Al H2O2, O4- by reaction with hydroxide ion. Al H2O3O3, letter 1d44, letter 1d45e, plus O-, letter 1d44, letter 1d45e, H2O, letter 1d459, plus Al, H2O2, O4-, letter 1d44, letter 1d45e. In this reaction, a proton is transferred from one of the aluminum-bound H2O molecules to a hydroxide ion in solution. The Al H2O3, O3 compound thus acts as an acid under these conditions. On the other hand, when dissolved in strong acids, it is converted to the soluble ion Al, H2O, 6,3+ by reaction with hydronium ion. 3H3O+, letter 1d44, letter 1d45e plus Al, H2O3, O3, letter 1d44, letter 1d45e Al, H2O, 63+, letter 1d44, letter 1d45e, plus 3H2O, letter 1d459 in this case. Protons are transferred from hydronium ions in solution to Al H2O3, O3, and the compound functions as a base. Learning objectives. By the end of this section, you will be able to predict whether a salt solution will be acidic, basic, or neutral. Calculate the concentrations of the various species in a salt solution. Describe the acid ionization of hydrated metal ions. Salts with acidic ions. Salts are ionic compounds composed of cations and anions, either of which may be capable of undergoing an acid or base ionization reaction with water. Aqueous salt solutions, therefore, may be acidic, basic, or neutral, depending on the relative acid-base strengths of the salt's constituent ions. For example, dissolving ammonium chloride in water results in its dissociation, as described by the equation. NH4Cl, letter 1d460, NH4+, letter 1d44, letter 1d45e, plus Cl-, letter 1d44, letter 1d45e. The ammonium ion is the conjugate acid of the base ammonia, NH3. Its acid ionization, or acid hydrolysis, reaction is represented by NH4+, letter 1d44, letter 1d45e, plus H2O, letter 1D459H, 3O plus, letter 1D44, letter 1D45E, plus NH3, letter 1D44, letter 1D45E, letter 1D43E, equals letter 1D43W slash letter 1D43B. Since ammonia is a weak base, Kb is measurable and cause 0, ammonium ion is a weak acid. The chloride ion is the conjugate base of hydrochloric acid, and so its base ionization, or base hydrolysis, reaction is represented by Cl minus, letter 1D44, letter 1D45E, plus H2O, letter 1D459HCl, letter 1D44, letter 1D45E, plus O minus, letter 1D44, letter 1D45E, letter 1D43B equals letter 1D43W slash letter 1D43E. Since HCl is a strong acid, Ka is immeasurably large and Kb approximately 0. Chloride ions don't undergo appreciable hydrolysis. Thus, dissolving ammonium chloride in water yields a solution of weak acid cations, NH4+, and inert anions, Cl-, resulting in an acidic solution. Example 14. 15. Calculating the pH of an acidic salt solution. Aniline is an amine that is used to manufacture dyes. It is isolated as anilinium chloride, C6H5NH3Cl, a salt prepared by the reaction of the weak base aniline and hydrochloric acid. What is the pH of a 233 m solution of anilinium chloride, C6H5NH3 plus letter 1D44, letter 1D45E, plus H2O, letter 1D459H3O plus letter 1D44, letter 1D45E, plus C6H5NH2, letter 1D44, letter 1D45E. Solution. The Ka for anilinium ion is derived from the Kb for its conjugate base, aniline C appendix I. Letter 1D43A equals letter 1D43W, letter 1D43B equals 1. 0 times 10 minus 144. 3 times 10 minus 10 equals 2. 3 times 10 minus 5. Using the provided information, an ICE table for this system is prepared. This table has 2 main columns and 4 rows. The first row for the first column does not have a heading and then has the following in the first column: initial concentration, M, change M, equilibrium M. The second column has the header of C subscript 6H subscript 5NH subscript 3 superscript positive sign plus sign H subscript 2 O equilibrium sign C subscript 6H subscript 5NH subscript 2 plus sign H subscript 3 O superscript positive sign. Under the second column is a subgroup of 4 columns and 3 rows. The first column has the following: 233, negative x, 233 minus x. The second column is blank for all 3 rows. The third column has the following: 0, positive x, x. The fourth column has the following: approximately 0, positive x, x. Substituting these equilibrium concentration terms into the Ka expression gives K letter 1D44E equals C, 6H5NH2H3O plus slash C, 6H5NH3 plus 2. 3 times 10 minus 5 equals letter 1D465, letter 1D465, slash 0. 233 minus letter 1D465. Assuming x 0, 233, the equation is simplified and solved for x. 2. 3 times 10 minus 5 equals letter 1D465 2 slash 0. 233, letter 1D465 equals 0. 23m. The ICE table defines X as the hydronium ion molarity, and so the pH is computed as pH equals minus log H, 3O plus equals minus log 0. 0023 equals 2. 64. Check your learning. What is the hydronium ion concentration in a 100 m solution of ammonium nitrate, NH4NO3, a salt composed of the ions NH4+, and NO3-, which is the stronger acid, C6H5NH3+, or NH4+? Answer: H3O+ equals 75 times 10 - 6 m, C6H5NH3+, is the stronger acid. Salts with basic ions. As another example, consider dissolving sodium acetate in water. NaCH3CO2, letter 1D460, Na plus, letter 1D44, letter 1D45E, plus CH3CO2 minus, letter 1D44, letter 1D45E. The sodium ion does not undergo appreciable acid or base ionization and has no effect on the solution pH. This may seem obvious from the ion's formula, which indicates no hydrogen or oxygen atoms, but some dissolved metal ions function as weak acids, as addressed later in this section. The acetate ion, CH3CO2-, is the conjugate base of acetic acid, CH3CO2H, and so its base ionization, or base hydrolysis, reaction is represented by CH3CO2-, letter 1D44, letter 1D45E, plus H2O, letter 1D459CH, 3-coat-H, letter 1D44, letter 1D45E, plus O-, letter 1D44, letter 1D45E, letter 1D43B equals letter 1D43W / letter 1D43E. Because acetic acid is a weak acid, its Ca is measurable, and Kb, acetate ion, is a weak base. Dissolving sodium acetate in water yields a solution of inert cations, Na+, and weak base anions, CH3CO2-, resulting in a basic solution. Example 14. 16. Equilibrium in a solution of a salt of a weak acid and a strong base. Determine the acetic acid concentration in a solution with CH3CO2- equals 0. 50 m and O- equals 25 times 10 - 6 m at equilibrium. The reaction is CH3CO2-, letter 1D44, letter 1D45E, plus H2O, letter 1D459CH, 3-co2H, letter 1D44, letter 1D45E, plus O-, letter 1D44, letter 1D45E. Solution: the provided equilibrium concentrations and a value for the equilibrium constant will permit calculation of the missing equilibrium concentration. The process in question is the base ionization of acetate ion, for which letter 1D43B for CH3CO2- equals letter 1D43W, letter 1D43A, for CH3-coat-H equals 1. 0 times 10 - 141, 8 times 10 - 5 equals 5, 6 times 10 - 10. Substituting the available values into the Kb expression gives letter 1D43B equals CH, 3-coat-HO minus CH, 3-co2- equals 5. 6 times 10 - 10 equals CH 3-coat-H 0. 6 times 10 - 10. Solving the above equation for the acetic acid molarity yields CH 3-coat-H equals 1. 1 times 10 - 5 m. Check your learning. What is the pH of a 0.83 m solution of NaCN? Answer: 11. Salts with acidic and basic ions. Some salts are composed of both acidic and basic ions, and so the pH of their solutions will depend on the relative strengths of these two species. Likewise, some salts contain a single ion that is amphiprotic, and so the relative strengths of this ion's acid and base character will determine its effect on solution pH. For both types of salts, a comparison of the Ca and Kb values allows prediction of the solution's acid-base status, as illustrated in the following example exercise. Example 14. 17. Determining the acidic or basic nature of salts. Determine whether aqueous solutions of the following salts are acidic, basic, or neutral. A. KBr. B. NaHCO3. C. NaHPO4. D. NH4F. Solution: consider each of the ions separately in terms of its effect on the pH of the solution, as shown here. A. The K+ cation is inert and will not affect pH. The bromide ion is the conjugate base of a strong acid, and so it is of negligible base strength, no appreciable base ionization. The solution is neutral. B. The Na+ cation is inert and will not affect the pH of the solution, while the HCO3- anion is amphiprotic. The Ca of HCO3- is 4. 7 times 10 - 11, and its Kb is 1. 0 times 10 - 144. 3 times 10 - 7 equals 2. 3 times 10 - 8. Since Kb Ca, the solution is basic. C. The Na+ cation is inert and will not affect the pH of the solution, while the HPO42- anion is amphiprotic. The Ca of HPO42- is 4. 2 times 10 - 13, and its Kb is 1. 0 times 10 - 146. 2 times 10 - 8 equals 1. 6 times 10 - 7. Because Kb Ca, the solution is basic. D. The NH4+ ion is acidic, see above discussion, and the F- ion is basic, conjugate base of the weak acid HF. Comparing the two ionization constants, Ca of NH4+, is 5, 6 times, 10 minus 10, and the Kb of F- is 1 6 times, 10 minus 11, so the solution is acidic since Ca Kb. Check your learning. Determine whether aqueous solutions of the following salts are acidic, basic, or neutral. A. K2CO3, B. KCl2, C. KH2PO4, D. NH4 2CO3. Answer A. Basic, B. Neutral, C. Acidic, D. Basic. The ionization of hydrated metal ions. Unlike the group 1 and 2 metal ions of the preceding examples, Na+, Ca2+, etc., some metal ions function as acids in aqueous solutions. These ions are not just loosely solvated by water molecules when dissolved. Instead, they are covalently bonded to a fixed number of water molecules to yield a complex ion. See chapter on coordination chemistry. As an example, the dissolution of aluminum nitrate in water is typically represented as AlNO33 letter 1d46 AlNO. However, the aluminum, Roman 3, ion actually reacts with 6 water molecules to form a stable complex ion, and so the more explicit representation of the dissolution process is AlNO33 letter 1d460 plus 6H2O letter 1d459 Al H2O 63 plus letter 1d44 letter 1d45E plus 3NO3 minus letter 1d44 letter 1d45E. As shown in figure 14. 13. The Al H2O 63 plus ions involve bonds between a central Al atom and the O atoms of the 6 water molecules. Consequently, the bonded water molecules O-H bonds are more polar than in non-bonded water molecules, making the bonded molecules more prone to donation of a hydrogen ion. Al H2O 63 plus letter 1d44 letter 1d45E plus H2O letter 1d459H 3O plus letter 1d44 letter 1d45E plus Al H2O 5O2 plus letter 1d44 letter 1d45E letter 1d43 equals 1. 4 times 10 minus 5. The conjugate base produced by this process contains 5 other bonded water molecules capable of acting as acids, and so the sequential or stepwise transfer of protons is possible as depicted in few equations below. Al H2O 63 plus letter 1d44 letter 1d45E plus H2O letter 1d459H 3O plus letter 1d44 letter 1d45E plus Al H2O 5O2 plus letter 1d44 letter 1d45E. Al HO H3O plus letter 1d44 letter 1d45E plus Al H2O4 O2 plus letter 1d44 letter 1d45E. Al H2O4 O2 plus letter 1d44 letter 1d45E plus H2O letter 1d459H 3O plus letter 1d44 letter 1d45E plus Al H2O3O3 letter 1d44 letter 1d45E. This is an example of a polyprotic acid, the topic of discussion in a later section of this chapter. A reaction is shown using ball and stick models. On the left, inside brackets with a superscript of 3 plus outside to the right is structure labeled Al H subscript 2O subscript 6 superscript 3 plus. Inside the brackets is S central gray atom to which 6 red atoms are bonded in an arrangement that distributes them evenly about the central gray atom. Each red atom has 2 smaller white atoms attached in a forked or bent arrangement. Outside the brackets to the right is a space-filling model that includes a red central sphere with 2 smaller white spheres attached in a bent arrangement. Beneath this structure is the label H subscript 2O. A double-sided arrow follows. Another set of brackets follows to the right of the arrows, which have a superscript of 2 plus outside to the right. The structure inside the brackets is similar to that on the left, except a white atom is removed from the structure. The label below is also changed to Al H subscript 2O subscript 5OH superscript 2 plus. To the right of this structure and outside the brackets is a space-filling model with a central red sphere to which 3 smaller white spheres are attached. This structure is labeled H subscript 3O superscript plus. Figure 14. 13. When an aluminum ion reacts with water, the hydrated aluminum ion becomes a weak acid. Aside from the alkali metals, group 1, and some alkaline earth metals, group 2, most other metal ions will undergo acid ionization to some extent when dissolved in water. The acid strength of these complex ions typically increases with increasing charge and decreasing size of the metal ions. The first step acid ionization equations for a few other acidic metal ions are shown below. Ph2O 63 plus, letter 1d44, letter 1d45e, plus H2O, letter 1d459H, 3O plus, letter 1d44, letter 1d45e, plus Ph2O 5O2 plus, letter 1d44, letter 1d45e, letter 1d45d, letter 1d43, equals 2. 74. Cu-H2O 62 plus, letter 1d44, letter 1d45e, plus H2O, letter 1d459H, 3O plus, letter 1d44, letter 1d45e plus, Cu-H2O 5O plus, letter 1d44, letter 1d45e, letter 1d45d, letter 1d43e, equals tilde 6. 3. ZnH2O 42 plus, letter 1d44, letter 1d45e, plus H2O, letter 1d459H, 3O plus, letter 1d44, letter 1d45e plus, ZnH2O 3. O plus, letter 1d44, letter 1d45e, letter 1d45d, letter 1d43, equals 9. 6. Example 14, 18. Hydrolysis of Al H2O 63 plus. Calculate the pH of a 010 m solution of aluminum chloride, which dissolves completely to give the hydrated aluminum ion Al H2O 63 plus. In solution. Solution. The equation for the reaction and Ka are Al HO. HO, H3O plus, letter 1d44, letter 1d45e, plus Al H2O 5O2 plus, letter 1d44, letter 1d45e, letter 1d43, equals 1. 4 times 10 minus 5. An ICE table with the provided information is. This table has 2 main columns and 4 rows. The first row for the first column does not have a heading and then has the following in the first column. Initial concentration, M, change M, equilibrium concentration, M. The second column has the header of a LH subscript 2O subscript 6 superscript 3 positive sign, plus H subscript 2O equilibrium arrow H subscript 3O superscript positive sign, plus a LH subscript 2O subscript 5. OH superscript 2 positive sign. Under the second column is a subgroup of 3 columns and 3 rows. The first column has the following: 010, negative X, 010 minus X. The second column has the following: approximately 0, positive X, X. The third column has the following: 0, positive X, X, substituting the expressions for the equilibrium concentrations into the equation for the ionization constant yields. Letter 1d43 equals H3O plus Al, H2O 5, O2 plus Al H2O, 63 plus, equals letter 1d465, letter 1d4650. 4 times 10 minus 5. Assuming x 0, 10, and solving the simplified equation gives letter 1d465 equals 1. 2 times 10 minus 3, letter 1d440. The ICE table defined x as equal to the hydronium ion concentration, and so the pH is calculated to be H3O plus equals 0, plus letter 1d465 equals 1. 2 times 10 minus 3, letter 1d440. pH equals minus log H3O plus equals 2. 92, an acidic solution. Check your learning. What is Al H2O5 O2 plus? In a 0,15 m solution of Al NO33 that contains enough of the strong acid HNO3 to bring H3O plus to 0. 10 m? Answer: 2 1 times. 10 minus 5 m. Learning objectives. By the end of this section, you will be able to extend previously introduced equilibrium concepts to acids and bases that may donate or accept more than one proton. Acids are classified by the number of protons per molecule that they can give up in a reaction. Acids such as HCl, HNO3, and HCN that contain one ionizable hydrogen atom in each molecule are called monoprotic acids. Their reactions with water are HCl, HO, HO, Cl, HNO, HO, HO, no, HCN, HO, H3O plus, letter 1d44, letter 1d45e, plus Cn minus, letter 1d44, letter 1d45e, even though it contains 4 hydrogen atoms. Acetic acid, CH3COOH, is also monoprotic because only the hydrogen atom from the carboxyl group, COOH, reacts with bases. This image contains 2 equilibrium reactions. The first shows a C atom bonded to 3 H atoms and another C atom. The second C atom is double bonded to an O atom and also forms a single bond to another O atom. The second O atom is bonded to an H atom. There is a plus sign, and then the molecular formula H subscript 2O in equilibrium arrow follows the H subscript 2O. To the right of the arrow is H subscript 3O superscript positive sign. There is a plus sign. The final structure shows a C atom bonded the three H atoms and another C atom. This second C atom is double bonded to an O atom and single bonded to another O atom. The entire structure is in brackets and a superscript negative sign appears outside the brackets. The second reaction shows CH subscript 3COOH. A Q plus H subscript 2O L at equilibrium arrow H subscript 3O, a Q plus CH subscript 3COO superscript negative sign, a Q. Similarly, monoprotic bases are bases that will accept a single proton. Diprotic acids contain 2 ionizable hydrogen atoms per molecule. Ionization of such acids occurs in 2 steps. The first ionization always takes place to a greater extent than the second ionization. For example, sulfuric acid, a strong acid, ionizes as follows. First ionization. H2SO4, letter 1D44, letter 1D45E, plus H2O, letter 1D459H, 3O plus, letter 1D44, letter 1D45E, plus HSO4 minus, letter 1D44, letter 1D45E, letter 1D43E, a 1 equals more than 1O2. Complete dissociation second ionization. HSO4 minus, letter 1D44, letter 1D45E, plus H2O, letter 1D459H, 3O plus, letter 1D44, letter 1D45E, plus SO42 minus, letter 1D44, letter 1D45E, letter 1D43E, a 2 equals 1. 2 times 10 minus 2, this stepwise ionization process occurs for all polyprotic acids. Carbonic acid, H2CO3, is an example of a weak diprotic acid. The first ionization of carbonic acid yields hydronium ions and bicarbonate ions in small amounts. First ionization. H2CO3, letter 1D44, letter 1D45E, plus H2O, letter 1D459H, 3O plus, letter 1D44, letter 1D45E, plus HCO3 minus, letter 1D44, letter 1D45E, letter 1D43 H2CO, 3 equals H, 3O plus HCO, 3 minus H2CO, 3 equals 4. 3 times 10 minus 7, the bicarbonate ion can also act as an acid. It ionizes and forms hydronium ions and carbonate ions in even smaller quantities. Second ionization. HCO3 minus, letter 1D44, letter 1D45E, plus H2O, letter 1D459H, 3O plus, letter 1D44, letter 1D45E, plus CO32 minus, letter 1D44, letter 1D45E, letter 1D43 HCO, 3 minus equals H, 3O plus CO32 minus HCO, 3 minus equals 4. 7 times 10 minus 11 KH to CO3 is larger than letter 1D43 HCO 3 minus by a factor of 104. So H to CO3 is the dominant producer of hydronium ion in the solution. This means that little of the HCO3 minus formed by the ionization of H to CO3 ionizes to give hydronium ions and carbonate ions. And the concentrations of H3O plus and HCO3 minus are practically equal in a pure aqueous solution of H2CO3. If the first ionization constant of a weak diprotic acid is larger than the second by a factor of at least 20, it is appropriate to treat the first ionization separately and calculate concentrations resulting from it before calculating concentrations of species resulting from subsequent ionization. This approach is demonstrated in the following example exercise. Example 14. 19 ionization of a diprotic acid, carbonated water, contains a palatable amount of dissolved carbon dioxide. The solution is acidic because CO2 reacts with water to form carbonic acid, H2CO3. What are H3O+, HCO3- and CO32- in a saturated solution of CO2 with an initial H2CO3 equals 0? 33 m, H2CO3, letter 1D44, letter 1D45E, plus H2O, letter 1D459, H3O plus, letter 1D44, letter 1D45E, plus HCO3-, letter 1D44, letter 1D45E, letter 1D43E, a 1 equals 4. 3 times 10 minus 7 HCO3-, letter 1d44, letter 1d45e, plus H2O, letter 1d459H, 3O plus, letter 1d44, letter 1d45e, plus co32 minus letter 1d44, letter 1d45e, letter 1d43e, a 2 equals 4. 7 times 10 minus 11 solution, as indicated by the ionization constants, H2CO3 is a much stronger acid than HCO3-, so the stepwise ionization reactions may be treated separately. The first ionization reaction is H2CO3, letter 1d44, letter 1d45e, plus H2O, letter 1d459H, 3O plus, letter 1d44, letter 1d45e plus, HCO3-, letter 1d44, letter 1d45e, letter 1d43e, a 1 equals 4. 3 times 10 minus 7, using provided information, an ICE table for this first step is prepared. This table has 2 main columns and 4 rows. The first row for the first column does not have a heading and then has the following in the first column: initial concentration, M, change M, equilibrium concentration, M. The second column has the header of H subscript 2 CO subscript 3, plus sign H subscript 2O equilibrium arrow H subscript 3O superscript positive sign plus sign HCO subscript 3 superscript negative sign. Under the second column is a subgroup of 3 columns and 3 rows. The first column has the following: 0.33, negative sign X, 0.33 minus sign X. The second column has the following: approximately 0, positive X, X. The third column has the following: 0, positive X, X substituting the equilibrium concentrations into the equilibrium equation gives KH2CO3 equals H3O plus HCO3 minus H2CO3 equals letter 1d465, letter 1d4650. 0.33 minus letter 1d465 equals 4. 3 times 10 minus 7, assuming x 0.33, and solving the simplified equation yields 2 times 10 minus 4. The ICE table defined x as equal to the bicarbonate ion molarity and the hydronium ion molarity. H2CO3 equals 0. 33 M H3 O plus equals HCO 3 minus equals 1. 2 times 10 minus 4, letter 1d440. Using the bicarbonate ion concentration computed above, the second ionization is subjected to a similar equilibrium calculation. HCO3 minus, letter 1d44, letter 1d45e, plus H2O, letter 1d459H, 3O plus, letter 1d44, letter 1d45e, plus co32 minus letter 1d44, letter 1d45e, letter 1d43 HCO 3 minus equals H, 3O plus co32 minus HCO 3 minus equals 1. 2 times 10 minus 4, co32 minus 1. 2 times 10 minus 4, co32 minus equals 4. 7 times 10 minus 11, 1. 2 times 10 minus 4, 1. 2 times 10 minus 4 equals 4. 7 times 10 minus 11, letter 1d440. To summarize, at equilibrium H2CO3 equals 0. 33 M, H3O plus equals 1. 2 times 10 minus 4. HCO3 minus equals 1. 2 times 10 minus 4, letter 1d440. Co32 minus equals 4. 7 times 10 minus 11, letter 1d440. Check your learning. The concentration of H2S in a saturated aqueous solution at room temperature is approximately 0. 1 m. Calculate H3O plus, HS minus, and S2 minus in the solution. H to S, letter 1d44, letter 1d45e, plus H2O, letter 1d459H, 3O plus letter 1d44, letter 1d45e, plus HS minus, letter 1d44, letter 1d45e, letter 1d43e, a 1 equals 8. 9 times 10 minus 8 HS minus, letter 1d44, letter 1d45e, plus H2O, letter 1d459, H3O plus, letter 1d44, letter 1d45e, plus S2 minus letter 1d44, letter 1d45e, letter 1d43e, a 2 equals 1. 0 times 10 minus 19. Answer. H2S equals 0, 1 m, H3O plus equals HS minus equals 0.94 m, S2 minus equals 1 times 10 minus 19 m. A triprotic acid is an acid that has 3 ionizable H atoms. Phosphoric acid is one example. First ionization. H3PO4, letter 1d44, letter 1d45e, plus H2O, letter 1d459H3O plus, letter 1d44, letter 1d45E, plus H to Po 4 minus, letter 1d44, letter 1d45E, letter 1d43, a 1 equals 7. 5 times 10 minus 3 second ionization. H to Po 4 minus, letter 1d44, letter 1d45E, plus H to O, letter 1d459H3O plus, letter 1d44, letter 1d45E plus HPO 42 minus, letter 1d44, letter 1d45E, letter 1d43, a 2 equals 6. 2 times 10 minus 8 third ionization. HPO 42 minus, letter 1d44, letter 1d45E, plus H to O, letter 1d459H3O plus, letter 1d44, letter 1d45E, plus Po 43 minus letter 1d44, letter 1d45E, letter 1d43, a 3 equals 4. 2 times 10 minus 13. As for the diprotic acid examples, each successive ionization reaction is less extensive than the former, reflected in decreasing values for the stepwise acid ionization constants. This is a general characteristic of polyprotic acids, and successive ionization constants often differ by a factor of about 105 to 106. This set of 3 dissociation reactions may appear to make calculations of equilibrium concentrations in a solution of H3PO4 complicated. However, because the successive ionization constants differ by a factor of 105 to 106, large differences exist in the small changes in concentration accompanying the ionization reactions. This allows the use of math-simplifying assumptions and processes, as demonstrated in the examples above. Polyprotic bases are capable of accepting more than one hydrogen ion. The carbonate ion is an example of a diprotic base because it can accept 2 protons, as shown below. Similar to the case for polyprotic acids, note the ionization constants decrease with ionization step. Likewise, equilibrium calculations involving polyprotic bases follow the same approaches as those for polyprotic acids. H to O, letter 1d459, plus Co 32 minus, letter 1d44, letter 1d45E, HCO 3 minus, letter 1d44, letter 1d45E, plus O minus, letter 1d44, letter 1d45E, letter 1d43B, 1 equals 2. 1 times 10 minus 4 H2O, letter 1d459, plus letter 1d43BCO, 3 minus, letter 1d44, letter 1d45E, H to Co, 3. Letter 1d44, letter 1d45E plus, O minus, letter 1d44, letter 1d45E, letter 1d43B, 2 equals 2. 3 times 10 minus 8. Learning objectives. By the end of this section, you will be able to describe the composition and function of acid, base buffers, calculate the pH of a buffer before and after the addition of added acid or base. A solution containing appreciable amounts of a weak conjugate acid-base pair is called a buffer solution or a buffer. Buffer solutions resist a change in pH when small amounts of a strong acid or a strong base are added. Figure 14. 14. A solution of acetic acid and sodium acetate, CH3COOH plus CH3 CuNa, is an example of a buffer that consists of a weak acid and its salt. An example of a buffer that consists of a weak base and its salt is a solution of ammonia and ammonium chloride, NH3 AC plus NH4Cl AC. 2 images are shown. Image on the left shows 2 beakers that each contain yellow solutions. The beaker on the left is labeled unbuffered, and the beaker on the right is labeled pH equals 80 buffer. Image B similarly shows 2 beakers. The beaker on the left contains a bright orange solution and is labeled unbuffered. The beaker on the right is labeled pH equals 80 buffer. Figure 14. 14a, the unbuffered solution on the left and the buffered solution on the right have the same pH, pH 8. They are basic, showing the yellow color of the indicator methyl orange at this pH. B, after the addition of 1 ml of a 0,1m HCl solution, the buffered solution has not detectably changed its pH, but the unbuffered solution has become acidic, as indicated by the change in color of the methyl orange, which turns red at a pH of about 4. Credit, modification of work by Mark Ott. How buffers work. To illustrate the function of a buffer solution, consider a mixture of roughly equal amounts of acetic acid and sodium acetate. The presence of a weak conjugate acid-base pair in the solution imparts the ability to neutralize modest amounts of added strong acid or base. For example, strong base added to this solution will neutralize hydronium ion, causing the acetic acid ionization equilibrium to shift to the right and generate additional amounts of the weak conjugate base, acetate ion. CH3 coat H, letter 1D44, letter 1D45E, plus H2, letter 1D459H3O plus, letter 1D44, letter 1D45E, plus CH3 coat 2 minus, letter 1D44, letter 1D45E, likewise. Strong acid added to this buffer solution will shift the above ionization equilibrium left, producing additional amounts of the weak conjugate acid, acetic acid. Figure 14. 15 provides a graphical illustration of the changes in conjugate partner concentration that occur in this buffer solution when strong acid and base are added. The buffering action of the solution is essentially a result of the added strong acid and base being converted to the weak acid and base that make up the buffer's conjugate pair. The weaker acid and base undergo only slight ionization, as compared with the complete ionization of the strong acid and base, and the solution pH, therefore, changes much less drastically than it would in an unbuffered solution. This figure begins with a chemical reaction at the top. CH subscript 3COOH, a Q plus H subscript 2OL, equilibrium arrow H subscript 3O superscript positive sign, a Q plus CH subscript 3COO superscript negative sign, a Q. Below the text is a figure that resembles a bar graph. In the middle are two bars of equal height. One is labeled CH subscript 3COOH, and the other is labeled CH subscript 3COO superscript negative sign. There is a dotted line at the same height of the bars, which extends to the left and right. Above these two bars is the phrase, buffer solution equimolar in acid and base. There is an arrow pointing to the right which is labeled add OH superscript negative sign. The arrow points to two bars again, but this time the CH subscript 3COOH bar is shorter than that CH subscript 3COO superscript negative sign bar. Above these two bars is the phrase, buffer solution after addition of strong base. From the middle bars again, there is an arrow that points left. The arrow is labeled add H subscript 3O superscript positive sign. This arrow points to two bars again, but this time the CH subscript 3COOH bar is taller than the CH subscript 3COO superscript negative sign bar. These two bars are labeled buffer solution after addition of strong acid. Figure 14. 15 buffering action in a mixture of acetic acid and acetate salt. Example 14. 20 pH changes in buffered and unbuffered solutions. Acetate buffers are used in biochemical studies of enzymes and other chemical components of cells to prevent pH changes that might affect the biochemical activity of these compounds. A. Calculate the pH of an acetate buffer that is a mixture with 0, 10 m acetic acid and 0, 10 m sodium acetate. B. Calculate the pH after 10 ml of 0, 10 NaOH is added to 100 ml of this buffer. C. For comparison, calculate the pH after 10 ml of 0. 10 m NaOH is added to 100 ml of a solution of an unbuffered solution with a pH of 4. 74. Solution A, following the ice approach to this equilibrium calculation, yields the following. This table has two main columns and 4 rows. The first row for the first column does not have a heading and then has the following in the first column. Initial concentration, M, change M, equilibrium concentration, M. The second column has the header of CH subscript 3CO subscript 2H, H subscript 2O equilibrium arrow H subscript 3O superscript plus sign, CH subscript 3CO subscript 2 superscript negative sign. Under the second column is a subgroup of 4 columns and 3 rows. The first column has the following, 0, 10, negative X, 0, 10 minus sign X. The second column is blank. The third column has the following, approximately 0, positive X, X. The fourth column has the following, 0, 10, positive X, 0, 10 plus sign X. Substituting the equilibrium concentration terms into the Ka expression, assuming X 0, 10, and solving the simplified equation for x yields letter 1d465 equals 1. 8 times 10 minus 5, letter 1d440, h3o plus equals 0, plus letter 1d465 equals 1. 8 times 10 minus 5, letter 1d440, ph equals minus log h3o plus equals minus log 1. 8 times 10 minus 5 equals 4. 74b, calculate the pH after 1. 0 ml of 0. 10 mNaOH is added to 100 ml of this buffer. Adding strong base will neutralize some of the acetic acid, yielding the conjugate base acetate ion. Compute the new concentrations of these two buffer components, then repeat the equilibrium calculation of part A using these new concentrations. 0. 0.010 L times 0. 10 mol Na01 L equals 1. 0 times 10 minus 4 mol NaOH, the initial molar amount of acetic acid is 0. 100 L times 0. 100 mol CH3 coat H, 1 L equals 1. Mol CH CoH, the amount of acetic acid remaining after sum, is neutralized by the added base is 1. 0 times 10 minus 2 minus 0. 0 1 times 10 minus 2 equals 0. 99 times 10 minus 2 mol CH3 coat the newly formed acetate ion, along with the initially present acetate, gives a final acetate concentration of 1. 0 times 10 minus 2 plus 0. 0 1 times 10 minus 2 mol Na CH3 Co2 compute molar concentrations for the two buffer components. CH3 coat H equals 9. 9 times 10 minus 3 mol 0. 101 L equals 0. 98 m Na CH3 Co2 equals 1. 0 1 times 10 minus 2 mol 0. 101 L equals 0. 100 m. Using these concentrations, the pH of the solution may be computed as in part A above, yielding pH equals 4. 75, only slightly different from that prior to adding the strong base. C. For comparison, calculate the pH after 10 ml of 0. 10 mNaOH is added to 100 ml of a solution of an unbuffered solution with a pH of 4. 74. The amount of hydronium ion initially present in the solution is H3O plus equals 10 minus 4. 74 equals 1. 8 times 10 minus 5, letter 1d440, mol H3O plus equals 0. 100 letter 1d43F. 1. 8 times 10 minus 5, letter 1d440 equals 1. 8 times 10 minus 6 mol H3O plus, the amount of hydroxide ion added to the solution is mol O minus equals 0. 0010 letter 1d43F, 0. 10 letter 1d440 equals 1. 0 times 10 minus 4 mol O minus, the added hydroxide will neutralize hydronium ion via the reaction H3O plus. Letter 1d44 letter 1d45E plus O minus, letter 1d44 letter 1d45E2 H2O, letter 1d459 the 1. One stoichiometry of this reaction shows that an excess of hydroxide has been added, greater molar amount than the initially present hydronium ion. The amount of hydroxide ion remaining is 1. 0 times 10 minus 4 mol minus 1. 8 times 10 minus 6 mol equals 9. 8 times 10 minus 5 mol O minus, corresponding to a hydroxide molarity of 9. 8 times 10 minus 5 mol O minus slash 0. 101 letter 1d43F equals 9. 7 times 10 minus 4 letter 1d440, the pH of the solution is then calculated to be pH equals 14. 0 minus PO equals 14. Log 7 times 10 minus 4 equals 10. 99 in this unbuffered solution, addition of the base results in a significant rise in pH from 4.74 to 10. 99 compared with the very slight increase observed for the buffer solution in part B from 4.74 to 4.75. Check your learning show that adding 10 ml of 0. 10 mHCl changes the pH of 100 ml of a 18 times 10 minus 5 mHCl solution from 4.74 to 3. Answer. Initial pH of 1. 8 times 10 minus 5 mHCl. pH equals minus log H3O plus equals minus log 1. 8 times 10 minus 5 equals 474 moles of H3O plus in 100 ml 1. 8 times 10 minus 5 m HCl, 1 8 times 10 minus 5 moles L times 0. 100 L equals 1 8 times 10 minus 6 moles of H3O plus added by addition of 1. 0 ml of 0. 10 m HCl, 0 10 moles L times 0. 10 L equals 1 times 10 minus 4 moles, final pH after addition of 10 ml of 0. 10 m HCl. pH equals minus log H3O plus equals minus log a total moles, H3O plus total volume equals minus log 1 mol. 8 times 10 minus 6 mol 101 ml, 1 L 1000 ml equals 3. Buffer solutions do not have an unlimited capacity to keep the pH relatively constant, figure 14. 16. Instead, the ability of a buffer solution to resist changes in pH relies on the presence of appreciable amounts of its conjugate weak acid-base pair. When enough strong acid or base is added to substantially lower the concentration of either member of the buffer pair, the buffering action within the solution is compromised. No alt text figure 14. 16. The indicator color, methyl orange, shows that a small amount of acid added to a buffered solution of pH 8 beaker on the left has little effect on the buffered system, middle beaker. However, a large amount of acid exhausts the buffering capacity of the solution, and the pH changes dramatically, beaker on the right. Credit. Modification of work by Mark Ott. The buffer capacity is the amount of acid or base that can be added to a given volume of a buffer solution before the pH changes significantly, usually by 1 unit. Buffer capacity depends on the amounts of the weak acid and its conjugate base that are in a buffer mixture. For example, 1 L of a solution that is 10 m in acetic acid and 10 m in sodium acetate has a greater buffer capacity than 1 L of a solution that is 10 m in acetic acid and 10 m in sodium acetate, even though both solutions have the same pH. The first solution has more buffer capacity because it contains more acetic acid and acetate ion. Selection of suitable buffer mixtures. There are 2 useful rules of thumb for selecting buffer mixtures. A good buffer mixture should have about equal concentrations of both of its components. A buffer solution has generally lost its usefulness when one component of the buffer pair is less than about 10% of the other. Figure 14. 17 shows how pH changes for an acetic acid acetate ion buffer as base is added. The initial pH is 474. A change of 1 pH unit occurs when the acetic acid concentration is reduced to 11% of the acetate ion concentration. A graph is shown with a horizontal axis labeled added ml of 0. 10 mNOOH, which has markings and vertical grid lines every 10 units from 0 to 110. The vertical axis is labeled pH and is marked every 1 unit beginning at 0, extending to 11. A break is shown in the vertical axis between 0 and 4. A red curve is drawn on the graph which increases gradually from the point 0, 4, 8 up to about 107, after which the graph has a vertical section up to about 111. The curve is labeled CH subscript 3 CO subscript 2H is 11% of CH subscript 3 co subscript 2 superscript negative. Figure 14. 17 change in pH as an increasing amount of a 0-10 m NaOH solution is added to 100 ml of a buffer solution in which, initially, CH3 CO2H equals 0. 10 m and CH3 CO2 minus equals 0. 10 m. Note, the greatly diminished buffering action occurring after the buffer capacity has been reached, resulting in drastic rises in pH on adding more strong base. Weak acids and their salts are better as buffers for pHs less than 7. Weak bases and their salts are better as buffers for pHs greater than 7. Blood is an important example of a buffered solution, with the principal acid and ion responsible for the buffering action being carbonic acid, H2CO3, and the bicarbonate ion, HCO3-. When a hydronium ion is introduced to the bloodstream, it is removed primarily by the reaction H3O+, letter 1D44 letter 1D45E, plus HCO3-, letter 1d44 letter 1d45e, H2CO 3, letter 1d44 letter 1d45e plus H2O, letter 1d459, an added hydroxide ion is removed by the reaction. O-, letter 1d44 letter 1d45e, plus H2CO 3, letter 1d44 letter 1d45e, HCO3-, letter 1d44 letter 1d45e, plus H2O, letter 1d459, the added strong acid or base is thus effectively converted to the much weaker acid or base of the buffer pair. H3O+, is converted to H2CO3, and OH is converted to HCO3. The pH of human blood thus remains very near the value determined by the buffer pair's pKa, in this case, 735. Normal variations in blood pH are usually less than 0.1, and pH changes of 0.4 or greater are likely to be fatal. The Henderson-Hasselbalch equation, the ionization constant expression for a solution of a weak acid, can be written as letter 1d43 A equals H3O plus A minus Ha, rearranging to solve for H3O plus. Yields H3O plus equals letter 1d43 A times Ha, minus taking the negative logarithm of both sides of this equation, gives minus log H3O plus equals minus log letter 1d43 A minus log Ha minus, which can be written as pH equals P letter 1d43 A plus log A minus Ha, where pKa is the negative of the logarithm of the ionization constant of the weak acid. pKa equals minus log Ka. This equation relates the pH, the ionization constant of a weak acid, and the concentrations of the weak conjugate acid-base pair in a buffered solution. Scientists often use this expression, called the Henderson-Hasselbalch equation, to calculate the pH of buffer solutions. It is important to note that the X is small assumption must be valid to use this equation. Portrait of a chemist Lawrence Joseph Henderson and Carl Albert Hasselbalch Lawrence Joseph Henderson, 1878–1942, was an American physician, biochemist, and physiologist, to name only a few of his many pursuits. He obtained a medical degree from Harvard and then spent 2 years studying in Strasbourg, then a part of Germany, before returning to take a lecturer position at Harvard. He eventually became a professor at Harvard and worked there his entire life. He discovered that the acid-base balance in human blood is regulated by a buffer system formed by the dissolved carbon dioxide in blood. He wrote an equation in 1908 to describe the carbonic acid-carbonate buffer system in blood. Henderson was broadly knowledgeable. In addition to his important research on the physiology of blood, he also wrote on the adaptations of organisms and their fit with their environments, on sociology, and on university education. He also founded the Fatigue Laboratory at the Harvard Business School, which examined human physiology with specific focus on work in industry, exercise, and nutrition. In 1916, Carl Albert Hasselbalch, 1874–1962, a Danish physician and chemist, shared authorship in a paper with Christian Boer in 1904 that described the Boer effect, which showed that the ability of hemoglobin in the blood to bind with oxygen was inversely related to the acidity of the blood and the concentration of carbon dioxide. The pH scale was introduced in 1909 by another Dane, Sorensen, and in 1912, Hasselbalch published measurements of the pH of blood. In 1916, Hasselbalch expressed Henderson's equation in logarithmic terms, consistent with the logarithmic scale of pH, and thus the Henderson-Hasselbalch equation was born. How sciences interconnect medicine. The buffer system in blood, the normal pH of human blood, is about 7, for the carbonate buffer system in the blood uses the following equilibrium reaction. Co, HO, H2CO3, letter 1d44, letter 1d45e. HCO3- letter 1d44, letter 1d45e, plus H3O+, letter 1d44, letter 1d45e, the concentration of carbonic acid, H2CO3, is approximately 0.12 m, and the concentration of the hydrogen carbonate ion, HCO3-, is around 0.24 m. Using the Henderson-Hasselbalch equation and the pKa of carbonic acid at body temperature, we can calculate the pH of blood. pH equals P letter 1d43, A plus log base acid equals 6, 4 plus log 0, 240, 0012 equals 7. 7. The fact that the H2CO3 concentration is significantly lower than that of the HCO3- ion may seem unusual. But this imbalance is due to the fact that most of the byproducts of our metabolism that enter our bloodstream are acidic. Therefore, there must be a larger proportion of base than acid so that the capacity of the buffer will not be exceeded. Lactic acid is produced in our muscles when we exercise. As the lactic acid enters the bloodstream, it is neutralized by the HCO3- ion, producing H2CO3. An enzyme then accelerates the breakdown of the excess carbonic acid to carbon dioxide and water, which can be eliminated by breathing. In fact, in addition to the regulating effects of the carbonate buffering system on the pH of blood, the body uses breathing to regulate blood pH. If the pH of the blood decreases too far, an increase in breathing removes CO2 from the blood through the lungs, driving the equilibrium reaction, such that H3O+ is lowered. If the blood is too alkaline, a lower breath rate increases CO2 concentration in the blood, driving the equilibrium reaction the other way, increasing H+, and restoring an appropriate pH. Link to learning view information on the buffer system encountered in natural waters. Learning objectives. By the end of this section, you will be able to interpret titration curves for strong and weak acid-base systems, compute sample pH at important stages of a titration, explain the function of acid-base indicators, as seen in the chapter on the stoichiometry of chemical reactions. Titrations can be used to quantitatively analyze solutions for their acid or base concentrations. In this section, we will explore the underlying chemical equilibria that make acid-base titrimetry a useful analytical technique. Titration curves. A titration curve is a plot of some solution property versus the amount of added titrant. For acid-base titrations, solution pH is a useful property to monitor because it varies predictably with the solution composition, and therefore may be used to monitor the titration's progress and detect its endpoint. The following example exercise demonstrates the computation of pH for a titration solution after additions of several specified titrant volumes. The first example involves a strong acid titration that requires only stoichiometric calculations to derive the solution pH. The second example addresses a weak acid titration requiring equilibrium calculations. Example 14. 21. Calculating pH for titration solutions. Strong acid, strong base. A titration is carried out for 25 ml of 0. 100 m HCl, strong acid, with 0. 100 m of a strong base, no OH. The titration curve is shown in Figure 14. 18. Calculate the pH at these volumes of added base solution. A 0 ml B 12, 50 ml C 25, ml D 37, 50 ml solution. A titrant volume equals 0 ml. The solution pH is due to the acid ionization of HCl. Because this is a strong acid, the ionization is complete and the hydronium ion molarity is 0. 100 m, the pH of the solution is then pH equals minus log 0. 100 equals 1. 0 B, titrant volume equals 12, 50 ml. Since the acid sample and the base titrant are both monoprotic and equally concentrated, this titrant addition involves less than a stoichiometric amount of base. And so, it is completely consumed by reaction with the excess acid in the sample. The concentration of acid remaining is computed by subtracting the consumed amount from the initial amount, and then dividing by the solution volume. H3O+ equals NH+, letter 1D449 equals 0. 2,500 mol times 1,000 ml 1L minus 0. 100 letter 1D440 times 12, 50 ml 25. ml plus 12, 50 ml equals 0. 333 mc, titrant volume equals 25 ml. This titrant addition involves a stoichiometric amount of base, the equivalence point, and so only products of the neutralization reaction are in solution, water and NaCl. Neither the cation nor the anion of this salt undergo acid-base ionization. The only process generating hydronium ions is the autoprotolysis of water. The solution is neutral, having a pH equals 7. D, titrant volume equals 37. 50 ml, this involves the addition of titrant in excess of the equivalence point. The solution pH is then calculated using the concentration of hydroxide ion. NO-0, NH plus 0, O- equals NO-, letter 1D449 equals 0. 100 letter 1D440 times 37. 50 ml minus 0. 2,500 mol times 1,000 ml 1L25. 0 ml. 50 ml equals 0. 200 m pH equals 14 minus POH equals 14 plus log, O minus, equals 14 plus log 0. 200 equals 12. 30 Check your learning. Calculate the pH for the strong acid strong base titration between 50 0 ml of 0. 100 m HNO3, AC, and 0. 200 m NOH, titrant at the listed volumes of added base. 0 ml, 15 0 ml, 25 0 ml, and 40. 0 ml answer, 0, 1. 0, 15 0, 150 111, 25 0, 7, 40 0, 12. 523 Example 14. 22 Titration of a weak acid with a strong base. Consider the titration of 25 ml of 0. 100 m CH3 CO2H with 0. 100 m NOH. The reaction can be represented as CH3 COH plus O minus CH3 CO2 minus plus H2O. Calculate the pH of the titration solution after the addition of the following volumes of NOH titrant. A0 mlB 25, mlC 12, 50 ml-D 37. 50 ml solution. A. The initial pH is computed for the acetic acid solution in the usual ice approach. Letter 1D43, A equals H3O plus CH, 3 CO2 minus CH, 3 coat H approximately H, 3 O plus 2 CH, 3 coat H0. And H3O plus equals letter 1D43 letter 1D44 times CH, 3 coat H square equals 1. 8 times 10 minus 5 times 0. 100 square equals 1. 3 times 10 minus 3 pH equals minus log 1. 87b. The acid and titrant are both monoprotic, and the sample and titrant solutions are equally concentrated. Thus, this volume of titrant represents the equivalence point. Unlike the strong acid example above, however, the reaction mixture in this case contains a weak conjugate base, acetate ion. The solution pH is computed considering the base ionization of acetate, which is present at a concentration of 0. 250 mol 0. 500 L equals 0. 500 mCH 3 CO2 minus base ionization of acetate is represented by the equation CH3 CO2 minus letter 1D44 letter 1D45E plus H2O, letter 1D459. CH3 CO2H letter 1D44 letter 1D45E plus O minus letter 1D44 letter 1D45E HO. 0 times 10 minus 141. 8 times 10 minus 5 equals 5. 6 times 10 minus 10, assuming x0. 500, the pH may be calculated via the usual ice approach. Letter 1D43b equals letter 1D465 20. 500 m letter 1D465 equals O minus equals 5. 3 times 10 minus 6 POH equals minus log 5. 3 times 10 minus 6 equals 5. 28 pH equals 14. 0, 0 minus 5. 28 equals 8. 72 Note that the pH at the equivalence point of this titration is significantly greater than 7, as expected when titrating a weak acid with a strong base. C. Titrant volume equals 12, 50 ml. This volume represents 1/2 of the stoichiometric amount of titrant, and so 1/2 of the acetic acid has been neutralized to yield an equivalent amount of acetate ion. The concentrations of these conjugate acid-base partners, therefore, are equal. A convenient approach to computing the pH is use of the Henderson-Hasselbalch equation. pH equals letter 1D45D letter 1D43. A plus log base acid equals minus log letter 1D43. A plus log CH 3 coat 2 minus CH 3 coat H equals minus log 1. 8 times 10 minus 5 plus log 1 pH equals minus log 1. 8 times 10 minus 5 equals 4. 74 pH equals pK at the half equivalence point in a titration of a weak acid. D. Titrant volume equals 37. 50 ml, this volume represents a stoichiometric excess of titrant, and a reaction solution containing both the titration product, acetate ion, and the excess strong titrant. In such solutions, the solution pH is determined primarily by the amount of excess strong base, O minus equals 0, 3,750 mol minus 0, 250 mol 0, 6,250 L equals 2. 0 times 10 minus 2 letter 1d440 POH equals minus log 2. 0 times 10 minus 2 equals 1. 70 and pH equals 14. 0 minus 1. 70 equals 12. 30 Check your learning. Calculate the pH for the weak acid strong base titration between 50 ml of 0, 100 m HQ AC, formic acid, and 200 m NaOH titrant at the listed volumes of added base 0 ml, 15 ml, 25 ml, and 30 ml. Answer 0 ml 237, 15 ml 392 25 ml 829, 30 ml 12 97. Performing additional calculations similar to those in the preceding example permits a more full assessment of titration curves. A summary of pH volume data pairs for the strong and weak acid titrations is provided in Table 14. 2 and plotted as titration curves in Figure 14. 18. A comparison of these two curves illustrates several important concepts that are best addressed by identifying the 4 stages of a titration. Initial state, added titrant volume equals 0 ml. pH is determined by the acid being titrated. Because the two acid samples are equally concentrated, the weak acid will exhibit a greater initial pH preequivalence point, 0 ml v 25 ml. Solution pH increases gradually, and the acid is consumed by reaction with added titrant. Composition includes unreacted acid and the reaction product, its conjugate base equivalence point, V equals 25 ml. A drastic rise in pH is observed as the solution composition transitions from acidic to either neutral, for the strong acid sample, or basic, for the weak acid sample, with pH determined by ionization of the conjugate base of the acid post-equivalence point, V 25 ml. pH is determined by the amount of excess strong base titrant added. Since both samples are titrated with the same titrant, both titration curves appear similar at this stage. pH values in the titrations of a strong acid and of a weak acid volume of 0. 100 m NaOH added, ml, moles of NaOH added pH value 0. 100 m HCl, 1 pH value 0. 100 m CH3 CO2H, 20000 10287 5118 4, 1410, 00 101 37 4, 5715, 00 151, 64, 9220, 00 201, 95 5, 35 22, 00 222 25 61 24, 00 242, 69 6 13 24, 50, 245 30 6 44 24, 90, 249 3, 77, 1425, 00 257 08, 72 25, 10 251 10, 30 10, 30 25, 50, 255 11, 0 11, 0 26, 00 260 11, 29 11, 29 28, 00 280 11, 75 11, 75 30, 00 311, 96 11, 96 35, 00 350 12, 22 12, 22 40, 00 412, 36 12, 36 45, 00 450 12, 46 12, 46 50, 00 512, 52 12, 52. Table 14. Two graphs are shown. The first graph on the left is titled Titration of Weak Acid. The horizontal axis is labeled Volume of 0. 100 mN, a OH added, mL. Markings and vertical grid lines are provided every 5 units from 0 to 50. The vertical axis is labeled pH and is marked every 1 unis beginning at 0, extending to 14. A red curve is drawn on the graph which increases steadily from the point 0, 3 up to about 25, 5, after which the graph has a vertical section from 25, 7 up to 25, 11. The graph then levels off to a value of about 12, 5 from about 40 ml up to 50 ml. The midpoint of the vertical segment of the curve is labeled equivalence point pH 872. The second graph on the right is titled Titration of Strong Acid. The horizontal axis is labeled Volume of 0, 100 mN, a OH added, ml. Markings and vertical grid lines are provided every 5 units from 0 to 50. The vertical axis is labeled pH and is marked every 1 units beginning at 0, extending to 14. A red curve is drawn on the graph which increases gradually from the point 0, 1 up to about 22.5, 22, after which the graph has a vertical section from 25, 4 up to nearly 25, 11. The graph then levels off to a value of about 12, 4 from about 40 ml up to 50 ml. The midpoint of the vertical segment of the curve is labeled equivalence point pH 7. Figure 14. 18a, the titration curve for the titration of 25 ml of 0. 100 m HCl, strong acid, with 0. 100 m NaOH, strong base, has an equivalence point of 7. pH B, the titration curve for the titration of 25 ml of 0. 100 m acetic acid, weak acid, with 0. 100 m NaOH, strong base, has an equivalence point of 8. 72 pH acid-base indicators certain organic substances change color in dilute solution when the hydronium ion concentration reaches a particular value. For example, phenolphthalein is a colorless substance in any aqueous solution with a hydronium ion concentration greater than 5 times 10⁻⁹ m, pH 8.3. In more basic solutions where the hydronium ion concentration is less than 5 times 10⁻⁹ m, pH 8.3, it is red or pink. Substances such as phenolphthalein, which can be used to determine the pH of a solution, are called acid-base indicators. Acid-base indicators are either weak organic acids or weak organic bases. The equilibrium in a solution of the acid-base indicator methyl orange, a weak acid, can be represented by an equation in which we use HN as a simple representation for the complex methyl orange molecule. Hin letter 1d44 letter 1d45e plus, H2 letter 1d459. Red H3O plus, letter 1d44 letter 1d45e, plus in minus, letter 1d44 letter 1d45e, yellow letter 1d43 letter 1d44e equals H3O plus in minus hin equals 4. 0 times 10⁻⁴, the anion of methyl orange in minus is yellow, and the non-ionized form, HN, is red. When we add acid to a solution of methyl orange, the increased hydronium ion concentration shifts the equilibrium toward the non-ionized red form, in accordance with Le Chatelier's principle. If we add base, we shift the equilibrium towards the yellow form. This behavior is completely analogous to the action of buffers. The perceived color of an indicator solution is determined by the ratio of the concentrations of the two species in minus and HN. If most of the indicator, typically about 60–90% or more, is present as in minus, the perceived color of the solution is yellow. If most is present as HN, then the solution color appears red. The Henderson-Hasselbalch equation is useful for understanding the relationship between the pH of an indicator solution and its composition, thus perceived color. pH equals p letter 1d43e a plus log in minus hin. In solutions where pH pK, the logarithmic term must be positive, indicating an excess of the conjugate base form of the indicator, yellow solution. When pH pK, the log term must be negative, indicating an excess of the conjugate acid, red solution. When the solution pH is close to the indicator pK, appreciable amounts of both conjugate partners are present, and the solution color is that of an additive combination of each, yellow and red, yielding orange. The color change interval, or pH interval, for an acid-base indicator is defined as the range of pH values over which a change in color is observed. And for most indicators, this range is approximately pK plus or minus 1. There are many different acid-base indicators that cover a wide range of pH values and can be used to determine the approximate pH of an unknown solution by a process of elimination. Universal indicators and pH paper contain a mixture of indicators and exhibit different colors at different pHs. Figure 14.19 presents several indicators, their colors, and their color change intervals. This figure provides a graphical representation of indicators and color ranges. A horizontal axis is labeled pH. This axis begins at 0 and increases by 1s up to 13. The left side of the graphic provides a column with the names of indicators. To the right of each indicator name is either one or two colored bars that are shaded according to the indicator color at various pH ranges. From the top, the first row is labeled crystal violet. The associated colored bar is yellow at its left end at a pH of 0 and changes to green and blue, moving right to its endpoint at a pH of 1.8. The second row is labeled cresol red. The associated colored bar is red at its left end at a pH of 1 and changes to orange and yellow, moving right to its endpoint at a pH of just over 2. A second bar to its right is yellow at a pH of around 7 and proceeds through orange to red at a pH of about 9. The third row is labeled thymol blue. The associated colored bar is red at its left end at a pH of nearly 1.2 and changes to orange and red, moving right to its endpoint at a pH of 2.8. A second bar begins in yellow at a pH of 8 and proceeds through green and blue to its end at a pH of around 9.1. The fourth row is labeled erythrocin B. The associated colored bar is red from a pH of 2.2 to its endpoint at a pH of 3.6. The fifth row is labeled 2,4-dinitrophenol. The associated colored bar is white at its left end at a pH of 2.6 and changes to yellow at its endpoint at a pH of 4. The sixth row is labeled bromophenol blue. The associated colored bar is yellow at its left end at a pH of 3 and changes to green and blue, moving right to its endpoint at a pH of 4.5. The seventh row is labeled methyl orange. The associated colored bar is red-orange at its left end at a pH of 4.2 and changes to yellow, moving right to its endpoint at a pH of 6.3. The eighth row is labeled bromocresol green. The associated colored bar is yellow at its left end at a pH of 3.8 and changes to green and blue, moving right to its endpoint at a pH of 5. For the ninth row is labeled methyl red. The associated colored bar is orange at its left end at a pH of 4.2 and changes to yellow, moving right to its endpoint at a pH of 6.3. The 10th row is labeled Eriochrome black tea. The associated colored bar is red at its left end at a pH of 5 and changes to purple and blue, moving right to its endpoint at a pH of 6.5. The 11th row is labeled bromocresol purple. The associated colored bar is yellow at its left end at a pH of 5.2 and changes to purple, moving right to its endpoint at a pH of 6.8. The 12th row is labeled alizarin. The first associated colored bar is yellow-orange at its left end at a pH of 5.7 and changes to red, moving right to its endpoint at a pH of 7.2. A second bar begins in red at a pH of 11 and changes to purple, then dark blue at its right end at a pH of 12. For the 13th row is labeled bromethymol blue. The associated colored bar is yellow at its left end at a pH of 6 and changes to green and blue, moving right to its endpoint at a pH of 7.6. The 14th row is labeled phenol red. The associated colored bar is yellow-orange at its left end at a pH of 6.8 and changes to orange and red, moving right to its endpoint at a pH of 8.2. The 15th row is labeled M-nitrophenol. The associated colored bar is white at its left end at a pH of 6.8 and changes to yellow, moving right to its endpoint at a pH of 8.6. The 16th row is labeled O-cresylphthalene. The associated colored bar is white at its left end at a pH of 8.3 and changes to red, moving right to its endpoint at a pH of 9.8. The 17th row is labeled phenolphthalein. The associated colored bar is white at its left end at a pH of 8 and changes to pink moving right to its endpoint at a pH of 10. The 18th row is labeled thymolphthalein. The associated colored bar is light blue at its left end at a pH of 9.3 and changes to a deep, dark blue moving right to its endpoint at a pH of 10. 5. The 19th row is labeled alizarin yellow R. The associated colored bar is yellow-orange at its left end at a pH of 10 and changes to red moving right to its endpoint at a pH of 12. Figure 14. 19. This chart illustrates the color change intervals for several acid-base indicators. A graph is shown which is titled Titration of Weak Acid. The horizontal axis is labeled Volume of 0, 100 mN, a OH added ml, and begins at 0 with markings every 5 units up to 50. The vertical axis is labeled pH and begins at 0 and increases by single units up to 14. A red curve is drawn on the graph. The curve begins at 0, 3 and passes through the points 5, 4, 1, 10, 4, 7, 15, 5, 20, 5, 5, and 22, 5, 6, after which it rapidly increases, forming a vertical section centered at the point 25, 8, 7. The rapid increase of the curve then levels off, and the curve passes through the points 30, 12, 35, 12, 4, 40, 12, 5, 45, 12, 6, and 50, 12, 6. A brown rectangle extends horizontally across the graph, covering the pH of 3 to 4, 2 range. To the right, this rectangle is labeled methyl orange pH range. A blue rectangle extends horizontally across the graph, covering the pH of 4.6 to 8 range. To the right, this rectangle is labeled litmus pH range. A purple rectangle extends horizontally across the graph, covering the pH of 8.4 to 10 range. To the right, this rectangle is labeled phenolphthalein pH range. The midpoint of the vertical segment of the curve is labeled equivalence point pH 872. Figure 14. 20 titration curves for strong and weak acids, illustrating the proper choice of acid-base indicator. Any of the 3 indicators will exhibit a reasonably sharp color change at the equivalence point of the strong acid titration, but only phenolphthalein is suitable for use in the weak acid titration. The titration curves shown in Figure 14. 20 illustrate the choice of a suitable indicator for specific titrations. In the strong acid titration, use of any of the 3 indicators should yield reasonably sharp color changes and accurate endpoint determinations. For this titration, the solution pH reaches the lower limit of the methyl orange color change interval after addition of ml of titrant, at which point the initially red solution would begin to appear orange. When 25 ml of titrant has been added, the equivalence point, the pH is well above the upper limit and the solution will appear yellow. The titration's endpoint may then be estimated as the volume of titrant that yields a distinct orange to yellow color change. This color change would be challenging for most human eyes to precisely discern. More accurate estimates of the titration endpoint are possible using either litmus or phenolphthalein, both of which exhibit color change intervals that are encompassed by the steep rise in pH that occurs around the 25 ml equivalence point. The weak acid titration curve in Figure 14. 20 shows that only one of the 3 indicators is suitable for endpoint detection. If methyl orange is used in this titration, the solution will undergo a gradual red to orange to yellow color change over a relatively large volume interval, 0.6 ml, completing the color change well before the equivalence point, 25 ml, has been reached. Use of litmus would show a color change that begins after adding 7-8 ml of titrant and ends just before the equivalence point. Phenolphthalein, on the other hand, exhibits a color change interval that nicely brackets the abrupt change in pH occurring at the titration's equivalence point. A sharp color change from colorless to pink will be observed within a very small volume interval around the equivalence point. Footnotes 1 titration of 25 ml of 0, 100 m HCl, 0 250 mol of HCl with 0, 100 m NaOH, 2 titration of 25 ml of 0, 100 m CH3 COTOH, 0 250 mol of CH3 CoToH with 0. 100 m NoH.